I'll say a few organizational words after the introduction of the head of the institute, Professor Holger. I will invite.
Okay, I can speak from here. Dear colleagues, first of all, welcome to this nice conference. The institute is happy and proud to host this conference. It is the first of series of 3 conferences held by Science Foundation. So we believe it will be a nice beginning. So I'm sorry for the technical delay in the beginning, but I believe it will be smooth and pleasant conference for all of you. So I wish you everything the best in the next days. Spend good time in Sofia, in the conference, and do the conference.
Before getting started to introduce them, I'll say that tomorrow there is a dinner. I will say more details then. There will be some coffee breaks. Maybe there will be some technical delays there too, because I mixed up a little bit the time, but I'm now contacting the company so they make it at the right moment. So I think it should be fine. And I'm also very happy and thankful that all of you made it here. For some it was easier, for some it was harder, but basically everybody managed to come, and I think it's a very good beginning for this series of conferences, especially for problem in Bulgaria, which has very long traditions, but I think we need a little bit of stimulus for the younger generation also to work on this. So, Martin, Chair.
Yeah, again, also welcome from my side, and I would like to take the opportunity to thank Martin Sabok and his team for organizing this event here. It was mainly done by him, so I was only assisting from abroad, so many thanks, Martin. Now I would like to welcome our first speaker in the first session. It's David Steinberg from University of Oxford, who is going to speak about quasi-stationary Monte Carlo methods. So it has a theoretical and an applied flavor, so I'm looking forward to your talk, David.
Let me be the first of the speakers to thank the organizers for having put together such an exciting program and organized all of this and gotten us all here together. So I'm going to be talking about a topic that is, so it's fairly new. It's a new idea in stochastic simulation, but as I think I'll try to make clear, it's also not so new. It turns out there aren't. It seems in some sense strikingly different from familiar approaches to simulating from random distributions, but it's not. It turns out there aren't that many different ways of doing that. So this new method ends up being interestingly similar to many traditional approaches. So how do I change those? Oh. Oh, yeah. Okay. Right. Okay, so possible to get rid of that audio settings. Right. So many, but perhaps not all of you, will be familiar with the problem of Bayesian estimation. So given a collection of observations from an unknown probability distribution in the prior distribution, on distribution, so for instance, a parametric distribution, we have the problem of calculating the posterior distribution. And so in general, there is what we call the Monte Carlo method, which interestingly was invented by Enrico Fermi in the 1930s to study neutron diffusion. I was reading about this. No one actually knows how he did it, and he wasn't using, there weren't any electronic computers. He seems to have, I mean, he did this sort of privately, like maybe he came up with results and would tell people about them, perhaps using just, convenient sources of randomness that were around. In any case, this is an approach to understanding probability that depends on the basic idea that knowing a distribution does not mean necessarily calculating a density or a distribution function. Knowing a distribution means being able to generate samples from it. So if you can generate samples from a distribution, you can essentially find out anything you want to know about a probability distribution by calculating averages based on a sample. If you have a sufficiently large sample, you will be able to approximate so if you have any test function, so completely describing the probability distribution means being able to describe the expectation of any test function, and you can approximate that by taking your samples and applying the functions and computing the average. Now, already in the very early days of doing this, and the first applications were in nuclear physics, and the big demands, somewhat embarrassingly for the field, came from the development of nuclear weapons at Los Alamos in the 1940s. You often end up with distributions that are actually so they involve very large sample spaces or continuous sample spaces where there is not a simple way of even computing an exact sample. And the reason, as many of you are familiar, is typically that you have a discrete distribution on a very large space, and the distribution is defined only in terms of relative probabilities. So you can say that, if you give any two elements of this very large space, you can say what the ratio is of probabilities between them. You can say that one is 5 times as likely as the other, but if you have spaces, with millions or billions or trillions or 10 to the 30th elements, there's no way you can actually write down a probability, much less go through the whole set and pick one out according to this probability. And this is, of course, particularly typical of the problem of Bayesian estimation, where the problems are defined. You have a data set, and regardless of the size of the data set, if you have a large parameter space, the probability you're aiming for is defined in terms of being proportional to a likelihood. So so all you can say is, again, right, the relative probability of two possible choices of parameters is proportional to the ratio of their likelihoods. Now, one approach that was very much tried in the 1940s and is still a valid approach is what's called rejection sampling, and the related method of important sampling. And the idea there is that we generate proposals from a similar distribution. So you find some there are distributions that are easy to sample from, even though they're on a very large space. So, for instance, if you're trying to generate from some statistical mechanics model with interacting particles, you can generate from a model where all of the sites are independent. So that was easy, and then what you do is you accept or reject that choice in proportion to whether the likelihood is higher or lower than the target likelihood. Now, so that works in principle. The problem is that, and this again was recognized already in the 1940s, you have what's called the curse of dimensionality, which is to say, as the dimension of the space, or as the size of the space you're searching for gets larger, these rejection ratios get smaller and smaller. The likelihood of accepting a proposal gets smaller, and you end up with an extremely inefficient algorithm that maybe has to search through thousands or millions or billions of samples before it gets one that can be accepted. And so these people, von Neumann, Ulam, Metropolis in the 1940s, thought about a different approach that somehow escapes this curse of dimensionality, which is you define a Markov chain whose stationary distribution is the target distribution. And then what you do is you wait some period of time, you run this Markov chain some number of steps, and then take the average after those steps have passed, and the idea being that the Markov chain will have come close to its stationary distribution, and then what you're getting are a sequence of samples approximately from that target distribution. So in general, the approach that they took was somehow you wanted to create a reversible Markov chain that satisfied where you could check the detailed balance equation. So basically, you define your target, then you have the flow from x to y in this Markov chain is equal to the flow from y to x, and that then will immediately demonstrate that pi is stationary distribution, and under fairly general conditions, you will have convergence to it, and then you can let it run. And in particular, the Metropolis-Hastings algorithm, which started at this time, says you can basically, it's very much like rejection sampling, but it's rejection sampling for steps of the Markov chain. You propose according to some arbitrary proposal distribution, and then you accept or reject the steps, essentially, depending on whether they take you to higher or lower regions of the target distribution. The Gibbs sampler, which swept through statistics in the 1980s and 90s, is another of these general approaches, which says if you want to sample from the posterior of the general distribution, what you can do is you can update the dimensions one at a time. You can update basically the distribution. You can sample from your parameters one at a time, and in taking them in sampling from the distribution, holding all the other parameters fixed, and this also generates a Markov chain, which has the desired posterior as the target. Now, there are a number of problems with this sort of approach. Because, this is the way with any new method. Yeah, you start out and it seems like we'll solve every problem, and it solves a lot of problems, but then immediately you start focusing on the cases that are difficult. But also statistical practice has changed, and so the problems we have to deal with often are not easily, these traditional methods often fail. And so there's been a lot of work over the last 30 years developing new Markov chain Monte Carlo methods for sampling from Bayesian posteriors. And one problem, which I'll be coming back to, is that these are the chains that used in traditional MCMC methods are always reversible. And reversible chains spend a lot of time covering the same ground, right? They're random walks, essentially. They go back and forth over the same, if they found a region they like, they'll just keep running over it. And that makes them fairly inefficient, right? In principle, once you found a region of high probability, you could just know that's a region of high probability and move on and explore other parts of the space. But reversible chains don't do it, and there's been a lot of work in the last 10 or so years on non-reversible dynamics, which have the advantage of that they can move more quickly through the space, sampling the space more broadly, but they're much harder to analyze in terms of even developing such methods that will actually it's took a lot longer to even develop sort of general tools like like the Metropolis Hastings algorithm. But also it's hard to do basic analysis of their convergence properties and so on. I want to take a very brief digression on the history of the Metropolis Hastings algorithm. Just because I recently was reading the original paper, which appeared in 1953, and this is called it's called the Metropolis Hastings algorithm. There were 5 authors on it, only one of whom is Metropolis, and then Rosenbluth and Teller and Teller. And interestingly, so there's some disagreement about who contributed what to this original paper, but there's general agreement that Ariana Rosenbluth did essentially all the programming. And she's a mostly forgotten figure. It's not clear what, if anything, Metropolis contributed. Some people say he was involved, some people say he only provided the computer time. But Ariana Wright, later Rosenbluth, so she completed her PhD in physics at Harvard at age 22. Then went to Stanford, married Marshall Rosenbluth, and then when they both went to Los Alamos and co-invented Markov chain Monte Carlo. She then left research after the birth of her first child, which I think is something to contemplate about progress or not in science. And and interestingly, she died of COVID in 2020, age 93. There was actually a brief obituary in the New York Times. And but I also know that according to Wikipedia, the Wikipedia article about the Metropolis Hastings algorithm, it says the algorithm was named for Nicholas Metropolis and W.K. Hastings, which is true, but it says they were co-authors of the 1953 paper, which is certainly not true. Hastings was still a student in 1953 in Canada, and Hastings generalized the algorithm in 1970. Some of that is also in the Wikipedia article, but anyway, I think it's interesting that someone wrote Hastings in as an author on this paper, and the actual authors got ignored, except for the one whose name was earliest in the alphabet, anyway. So let me now talk about Langevin Monte Carlo which is well, it's an algorithm that in its basic form is also reversible, although there are non-reversible versions of it. So it's based, but it is it is in principle a continuous time algorithm. So the idea is that if you have a target distribution, if you look at, so if you have a target density that is, can be written as e to the minus u of x, and so u of x you can think of as being a log likelihood, then the Langevin diffusion with drift given by the gradient of u has this density as a stationary distribution. Now, so this is a continuous time algorithm, and in principle you can add an extra term onto this, which will make it a without changing the stationary distribution. You can make this a non-reversible model. It is, in any case, continuous time, which gives it some advantages, some of the advantages of non-reversible approaches, but in order to simulate it, right, the only thing people have been able to do is to apply the Euler discretization and effectively turn it back into a discrete time model. This produces what's called the unadjusted Langevin algorithm. So you pick some step size, and then you take some step according to the current drift, go some little bit of time, and then move on. This was first proposed in physics in the 1980s and entered statistical theory and practice in the 1990s, the work of Roberts and Tweedy. And it's known to be ergodic. There are good bounds on convergence, which I'll come back to. But of course, the discretization means that there's a bias that's introduced. The stationary distribution that it's targeting is not actually pi. And so there's a trade-off between computational cost and accuracy. If you choose a small gamma, it's going to take longer to compute, but you'll have less bias. If gamma's larger, you'll have increasing bias, and in fact, if it's large enough, then the model becomes unstable. The bias can be corrected. It was proposed by Bessa in 1994, using by essentially at every step you also right. So you're proposing a step according to these Langevin dynamics, but you might accept or reject them using the Metropolis algorithm, and thus you can end up targeting the right distribution. But you still end up with some significant problems. So sorry, I wrote it at the end. I didn't complete this sentence. So work by Otobra on the problems created by the reversibility of this algorithm. He proposed to add an extra term to make it non-reversible. But other problems are, well, as usual, we don't know how close. It's hard to know how well it's converged, and the computational cost of computing at every step you need to compute the log likelihood, and if you have a very large data set, then the cost of computing once is proportional to the number of dimensions times the number of samples, and that can be huge in data sets that statisticians often need to deal with these days, like in the millions, billions, trillions of entries that need to run through at every step, and it takes very many steps, right? And on top of this, if the dimension is more than 1 or 2, it will take a long time, many steps to converge. So D comes in to be, the dimension comes in in another way. So these algorithms, while in principle correct, can be impractical. Welling and Tay in 2011 proposed what's called the stochastic gradient Langevin dynamics, where you replace U by an unbiased estimator. The idea is that U is typically a log likelihood. It's a sum over potentially a very large number of terms. And so their proposal is that at every step when you need to compute the gradient, and so you need to compute U, or actually, would be, the gradient, you instead just take a small sample of the, from the entries, and only take the average of those and then multiply that by n to get an estimate of the true gradient. Now, of course, that's going to be an approximation to the dynamics, and the question is how close is it going to be, and introducing an additional error to the target distribution. For various technical reasons, you can't really do this metropolis adjustment to this. You can't do it in some sense because you can't. It won't be exact because you don't know since you haven't looked at all the entries. You don't actually know what the target density is. But and in fact, later work showed that in order for this to sort of be close enough to be usable, you really need to have order of capital N samples. So, the savings might be, the order of a factor of 2 or even a factor of 10, but that's not enough to make this really helpful in solving the problem of large data sets. So Pollack, Fernhead, Johansson, and Roberts in 2016, although actually published formally in 2020, proposed an alternative algorithm, and this is going to be the basis of what I'll be talking about, what they call the scalable Langevin exact algorithm, or SCALE, which is based on quasi-stationary convergence of the Kills process conditioned on survival. So the idea is that, instead of creating a Markov chain or Markov process, and typically a discrete time chain that has the target as its stationary distribution, you create a continuous time diffusion that is killed at some rate. And we are conditioned on survival for a long time. It has the target as its quasi-stationary distribution. So in other words, if you run it for a very long time, a particle that survives will be a sample from the stationary, from this quasi-stationary, let's say, the target distribution. Now, the advantages, and I'll explain why it has its advantages in a moment, is it has zero discretization error and zero bias due to subsampling. And it's fairly easy to compute, so pi is the target density. And so you take log pi, which for a Bayesian algorithm again is the log likelihood, and the killing can be computed in terms of the gradient and the velocity of this log likelihood. You need this killing rate to be bounded below by some k, which is non-zero. So it can't be this can't go to minus infinity, basically. But otherwise, you can define it. So if you then start with a Brownian motion, killed at rate given by this kappa tilde minus its lower bound, so basically make the minimum killing rate 0. This has unique quasi-stationary distribution, which is the target density. And this is quasi-limiting. So if you start the process and condition at any point and condition on survival longer than time t, as t goes to infinity, the distribution, the conditional distribution of the particle will converge to the target. And you can simulate this with a Fleming-Biot time particle filter, which is to say that you start with some moderate number of particles, typically on the order of 1,000, and you let them run according to this killed Brownian motion. But when they're killed, you resample from the population of particles. And of course, you'll notice now that after having talked about it having be exact and having zero bias and zero discrimination, somehow this particle filtering is going to introduce approximations into it again, right? So that there's not entirely a free lunch, but let me explain a bit about where this exactness comes from, because it's a brilliant discovery that those authors made, that you can do this exact sampling. Right, that in some sense this sort of process of killing is somehow fundamentally different from drift in this respect. So to begin with, so there's no drift. We can simulate exactly from Brownian motion, and if you give me some sequence of times, it's very easy to simulate the conditional distribution of the Brownian motion started at a particular point at those times. Furthermore, we can simulate exactly from killed Brownian motion without ever having to integrate the killing rate using Poisson infinity. So the idea is, so suppose we have some upper bound on the killing rate. So if we want to start at a point x and simulate t time units from the process started at x, what we do is we first simulate a Poisson process on the interval 0 to t with rate k, yielding some sequence of event times. So maybe we have 2 events according to this Poisson process. And then we only need to simulate the Brownian motion at those times, right? We just need to know where was the Brownian motion, or where would it have been at those 2 times. And at the end. And then we simulate points, so we simulate points from that Brownian motion, and then we kill it at time ti with probability basically proportional to the fraction of the killing rate that it actually had at that time. So that, right, that's how we can simulate from a non-homogeneous Poisson process. Furthermore, and this is something that was known before, that Roberts had worked on, particularly in the 1990s. But suppose we don't know, right? The whole problem that we were dealing with was that the killing rate, just like the drift in the Langevin algorithm, requires that we do a calculation on the entire data set. So that, again, that would be prohibitive if we had to do that at every step. But, and this is quite a striking, simple observation. What we're trying to do is to simulate a Bernoulli variable with a particular probability. But in some sense, right, there aren't that many ways to simulate a Bernoulli variable, and there's not really any way to bias a Bernoulli variable. So if instead of knowing the right probability, you instead know an unbiased sample, an unbiased estimate of the probability, and then you simulate that unbiased estimate and then simulate a Bernoulli variable with that probability, that is also a Bernoulli variable with the desired probability. So the result is that so all you need to do, you don't even need to take a big sample. You can just take a single uniform sample from your data set, compute the killing based on that one sample, and then compute the Bernoulli variable with that probability. And not only does that allow you to more simply with much less computational cost compute these discrete these outcomes, but you can it also easily allows you to parallelize the algorithm. Right, so to compute it on separate computers which have access to which will be separately accessing the data. Now, that said, so it seems like a brilliant algorithm. Like many brilliant algorithms, there's a question: does it work? And they have in the original paper there are 5 examples that are presented. None of them is entirely satisfying. So one example that illustrates the kind of problem involved is this large data set with 123 million commercial flights within the USA over the course of about 2 decades. And posing the problem of doing logistic regression to predict flight delay using 3 covariates plus an intercept, so 4 parameters. So whether it's a weekend flight, whether it's a night flight, and the distance. And they use 2 to the 12 particles, so about 4,000 particles, and run until every data point is sampled once. Okay, so rather than the naive algorithm where you would have to sample every data point at every round of the algorithm, they essentially only ran it as long as to fit with sampling each data point once. But the result is, so they confirmed that the normal approximation, the GLM, the result given by the GLM, standard GLM algorithm is basically right. And also, I noted they actually initialized the algorithm from that normal GLM fit. So it's a bit of what this example is saying is if you start from the right, knew the right answer to begin with, this algorithm, the scale wouldn't mess it up. In that respect, it is at least better than the stochastic gradient Langevin dynamic, which do mess it up. So so these 2 are binary covariates. The continuous covariate distance, so this is the intercept. These are the weekend and night, and this distance. So the green here, I don't know if you can see it, is the result of the SGLE algorithm, and it produces a very non-convex and incorrect sort of density, even when initialized at the right point. But still, obviously, it's not entirely convincing to say that this is a good Bayesian algorithm. If you start it in the right distribution, it will stay there. A somewhat similar simulated data set. So this is where you basically have a mixture of a lot of data that came from a normal model, right? So the outcome yi has normal errors and some parameters alpha and beta, that predicted from two covariates, X1, XI1, and XI2, but then some fraction P of the data actually have nothing to do with the X's. So they're kind of contaminating the mixture, and so they simulated this with 5% of the data being sort of incorrect in this way. And this time they did start the model at, not in the right distribution, but at some other point. But they started it very close to the true numbers, although not so close from the perspective of the sort of true posterior distribution. So here's what they and furthermore, the model did somewhat well, but not incredibly well. So the true value is in green, and the red is the result of the mean posterior that was calculated. And you can see that for most of the parameters, it did get closer to the true mean than where it started. I mean, it definitely didn't get stuck at its starting point or anything like that, and it didn't move in the wrong direction. But particularly like P, it didn't actually, like here, it still stayed pretty far away from the true value. So it's not entirely convincing that this is performing well. Yeah, so I need to move on. So sorry, this is going more slowly than I thought. So this is work that I was involved with, along with Martin Kolb and my graduate student Andy Wang, which was, and with Gareth Roberts as well. The idea being we wanted to generalize the scale model to allow for other underlying so instead of using just Brownlee motion, to have other diffusions as the basic motion that could then be killed to converge. So for instance, an Ornstein-Uhlenbeck process, something that you could simulate, and also to understand better the conditions under which the scale algorithm will converge. So here are the conditions we came up with. So we have a smooth target density and a smooth potential that's driving the underlying motion. And we have to assume this condition that the density, so even the 2A of y would be the invariant density would be proportional to the 2A of y. So we have this condition which essentially means that the density, the target density with respect, and we're doing everything with respect to this invariant density, this invariant distribution. So the target density with respect to that distribution it should have finite variance. And anyone who's familiar with importance sampling will know that this is a condition that will be required essentially for importance sampling to work. Right? If you wanted to sample the distribution pi using this invariant e to the 2A distribution as the reference measure, you need to have finite variance for this ratio. So it makes sense that you're not likely to be able to do much if you don't, like essentially if the tails of the distribution that you're trying to sample from are fatter than those of the distribution you're using essentially as reference. And then we have to compute filling rates according to this formula. And again, you might notice it's still linear in the target density. And we're going to kill the process at a rate given by essentially this rate, just pushed up to make it positive. And you might note that this killing rate can be expressed essentially as a measure of the difference between the target density and the invariant density of the underlying motion. So effectively, this is saying that you're killing the process when it is far away from the target. Okay, so the questions that this raises are, right, defined in Kapp's formula tells us the target distribution is quasi-stationary, but is it quasi-limiting? Do we actually have convergence to this target? And in other words, is the probability of being in set E conditioned on survival for a long time equal to this target? We wonder how fast does the process converge, and right, so the convergence rate is determined by the spectral gap of the diffusion operator. That's the kind of basic fact about reversible processes that makes them useful to deal with. So we'd like to understand the spectral gap and how can we realize the approach in a computationally efficient algorithm. And I'm not going to be able to say as much as I wanted to about the underlying theory. So that's in our 2019 paper. Fundamentally, the real point of this line is that we're going to mostly avoid using the heavy machinery of operator theory for proving convergence by appealing to this theory that Richard Tweedy invented back in the 1970s, which is sometimes called R theory. And it's a kind of fascinating probabilistic theory of positive semigroups. And the idea is he defines what's called it's sort of a generalization of the notion of transience and recurrence, or actually the definition go back to Beer Jones in the 60s. So we know that, right, transience means that the sum of this occupation measure, so we coin this occupation measure, this total occupation measure, G of XA, if you have Z1, then, right, transience means that sum is finite. And so by turning this into a power series, allowing Z to be chosen arbitrarily, this allows you to basically look for the kind of the edge, right, the boundary between transience and recurrence, which is basically given by the rate of this, and the notion of positivity, of being positive recurrent, turns out to translate into the question of whether on the boundary the associated R invariant measure gives a finite integral with the R invariant function. So on the boundary there will always be an invariant measure, an invariant function, and that's so we developed this theory that allows you to look at this notion of R positivity, and it turns out R positivity is exactly what you need for quasi-limiting behavior. And he generalized it, sorry, I'm go enough into explaining this in detail. I apologize. I prepared a bit too much material. So essentially by discretizing the continuous time process. So the idea is that that you're going to take some arbitrarily small interval h and look at this continuous time process in discrete steps. And essentially, if you can simultaneously have this positivity for so this positive recurrence for every one of these skeletons, these H skeletons, you can show that it's essentially positive recurrent at this, not at rate 1, but at this higher rate, which essentially is equivalent to quasi-limiting convergence. So lambda positivity, again, this is a notion that Tweedy introduced in the 70s. As far as I can tell, it's been impossible. It's a beautiful theory, but it turns out to be very impractical for most purposes. But it turned out to work well for this application. Sorry, and so anyway, so this positivity, R positivity, turns out to be easy, relatively straightforward to check for this kind of diffusion that we set up here, and so we immediately get this rate of convergence. We get convergence, and now the rate of convergence is given by the spectral gap, the gap between the first and second eigenvalues. And the one thing we have to say about the spectral gap is that it turns out to be exactly the same as, I didn't even say here what I meant by LZ. So the spectrum of the Langevin diffusion. And that's useful because there's been a lot of work on the spectrum of Langevin diffusion. So, essentially, right, the top eigenvalue, depending on how you turn it, and the bottom eigenvalue of Langevin diffusion is 0 because it's a Markov process, and but it's so the second eigenvalue, so something that describes the rate of convergence of Langevin diffusion, turns out to be exactly the same spectral gap that will apply to this general scale algorithm. Okay, so I'm running out of time, and I want to say at least a little bit about two alternatives to scale. So I'll just say the outline of this. So one problem with scale. One problem with scale is that it depends on this particle filter. You have to choose all the particles, follow them all this time. In particle filter applications, you always have the danger of the particles and the particle distribution can become singular. You lose diversity in the particles, and it's something that produces something that's arbitrary in the algorithm. There's an approximation that's involved in choosing a particular number of particles. So there were questions about whether scale could be run using only a single particle. And so now you run it until it's killed, and then the problem is, of course, you need all the other particles for it to decide where it gets reborn. And the idea is the idea of rescale is you remember the past of this one particle, and when it has to be reborn, it simply chooses a point from it basically jumps back to a point, maybe uniformly chosen or chosen according to some kind of discounting rate from its own past. Another proposal that was made, which is called randomly exploring the stochastically regenerating process, restore, is you simply fix a process, fix a distribution where the process will be reborn when it's killed. So the so-called regeneration measure. And this turns out actually to be quite a lot like other non-reversible MCMC methods, like so there are a lot of methods that have been proposed in recent years where you essentially have a piecewise deterministic motion, and the randomness or the effect of the target comes in that you, at random times, when it feels like it's moving into a bad neighborhood, it changes direction. So here, instead of changing direction, we have these non-reversible jumps. And I don't have time to go to any of the details. All I'm going to say is that these are done with very different methods. These are analyzed with very different methods. Rescale, you have this whole history of the process, which is a kind of whole past occupation measure. It's resampling from its own occupation measure. So you have to think of this as a random dynamical system on occupation measures and show that those converge. The restore is done with more traditional sort of stochastic process methods, but it turns out to be potentially more useful as a way of sort of like the way the metropolis adjusted Langevin work. You start with a process that's maybe not quite right or is mixing too slowly, and you sort of tune it up by adding these regeneration steps that are kind of non-reversible and might improve the dynamics. Okay, so sorry, we couldn't say more about these mathematical details there. Let me just conclude by saying, so quasi-stationary Monte Carlo offers an alternative paradigm for constructing sampling algorithms. And so we now have mathematical theory, we know how to create processes with provably correct properties, the right target distribution, geometrically orthotic, and all of that. But in some cases, there are non-reversible continuous time processes with some of the nice properties of reversible discrete time processes. But the simulated versions, when we actually try to realize them, they end up looking a lot like some of the traditional processes that we've done. And it's not yet clear what the best way is to turn these processes into efficient algorithms. And there are a lot of open questions. A lot of what's going on in statistical computing is about approximate Bayesian computation. Why are we obsessed to deal with exactness? What are the best ways to tune the algorithm for a particular problem? How do we choose the underlying notion to optimize convergence? And are there advantages for one of these approaches over the other? So that's all. Thank you very much.
Thank David for the talk. Are there any questions, comments about the topic of the talk? Yes, please.
So, since you assume spectral gap, is it in practice that you require pi to have compact support somehow?
No, it does not require compact support. Actually, this is work that actually Martin and I did in 2012 on one-dimensional diffusions. So in some sense, this isn't exactly true, but you'll have a spectral gap if the underlying process is positive recurrent. Yeah, and possibly it's slightly more complicated than that, but certainly if it's a positive recurrent process, you will have a spectral gap, and this is something that's known also from the lunchtime dynamics. Yes, please.
I really enjoyed it. I have two questions. Mathematical question and a silly question. The mathematical question is, what happens if you, in the settings with rescale, you just resample from exactly where you died? Equivalently, instead of killing, you just have a Poisson clock with a spatially dependent rate, and you just record the points where it ran. And then my silly question is, what did you mean when you said convenient? You were talking about, I think, Fermi studying simulations before computers existed. What do you mean when you said that? What would you speculate when you said convenient sources of randomness?
Yeah, well, convenient sources. So I'll start with the silly question. I think so. I've seen again. Nothing. I think my impression is it's not really known what he did, but I know people have speculated that he used coin flipping cards. A particular card. It seems to have used cards for. And now I've forgotten the mathematical question. What was it?
Rescheduling, you sample exactly where you start exactly where you died.
Well, if you start exactly where you died, you haven't really killed it, have you?
Yeah, exactly.
Yeah. So then right. So then you're just doing the. It's not a kill process. You're tracking the original. You just have your original motion.
So I guess my question is, if you record the points where you died and were originally immediately reborn, does this look like the station? No, I don't think there's any reason why it would be, but that seems like a very different. It seems like an so you imagine you said. So essentially, so then that's not really killing, right? So what it is it's taking a process and doing a sort of biased sampling of it according to some measure. And yeah, I don't know what that does. That sounds like actually a different approach to trying to. My guess is that gets you into. Kind of back more into the area that's more like importance sampling, where you'd probably be back to having a kind of closer dimensionality, right? Because the process is spending a lot of its time in a region that actually isn't good for this process.
Okay, further comments or questions? Otherwise, let's thank the speaker again today. But I can give you science now. Okay, the next speaker is Oliver Taff from University of Neuchâtel, but soon from University of Bath, and he's going to talk about random switching between ordinary differential equations and associated invariant solutions. So once it works, we're gonna start with your talk. Oliver, thanks for coming to Sofia.
Okay, so thanks to the organisers. So today we're going. So I should say all this is joint work with Michel Benaï. It's based on this archive preprint. So today we're talking about what got variously often called piecewise deterministic Markov processes or PDMPs. Basically, so what's the setup? We have a spatial variable xt, and we have a state variable it. And so we think about the state variable. It is sort of the source of the randomness, so it's just a jump process on one sort of set of states, 1 to n. And corresponding to each I, there's a vector field here. and we're going to just assume it's C infinity. And so each of these we can associate each of these vector fields in ordinary differential equation, right? So, and describing position-dependent movements from position-dependent velocity. So, when we combine these, we can get a random process where the randomness comes from this jump process, and then that drives randomness because you're switching between different vector fields, and whichever vector field you go is the velocity of your spatial movement. So, in the picture, we have here an example with two vector fields. So, we're here in blue and red, so you little bit with the blue vector field, you switch, you go along the red, you switch back blue, red, blue, red. And so you're switching between different flows, and whichever flow you're in is deterministic, which is why they're often called piecewise deterministic, because here they are piecewise deterministic. So the history, so in extremely general formulation, much more general than the formulation we're talking here, they were introduced by Davis in '84. So for a survey on what I'm talking about today, Malu has a survey from about 10 years ago, and there's a sort of historical account by Hirsch. And so just an example of a more complete example of a system we're interested here. So for Benaim and Lowy from about 6-7 years ago, they considered switching between Lotka-Volterra. So Lotka-Volterra models deterministically the change in the population of different species. And you think about random changes in the environment, changing the parameters of your ordinary differential equation. And so you're switching between different environments. Each of the environments corresponds to a version of the ODE, and then you want to know how does environmental change affect the population size in the long term. But this is sort of a specific example. So, what are we going to be interested in? So we've got this type of process, or this family of processes, and we're going to be interested in the kind of qualitative properties of the spatial distribution. So you have general results on the existence and uniqueness in convergence to the spatial distribution and the sort of Horn-Mander conditions. So it exists. So this is a kind of well-defined question. And so we're interested in the properties of the spatial distribution. So what do we know? So we know it's a probability measure on R to the D across 1 to n. R to the D is obviously the spatial bit, and 1 to n is your space bit. And it has a density, and we call it spatial density. And so I guess we're saying kind of a classical question is when is it smooth, right? So when do you have nice regularity in the spatial density? So for diffusions, obviously this is very, very well known, but for this, no, not so much. However. And so I've got to basically answer the question of when is pi smooth and bounded. Okay, so just to go through maybe a bit of basic stuff here, but to reflect on what we do with the diffusions and what goes along here. So for diffusions, the spatial density is it's uniform elliptic, then it's a second order uniform elliptic PDE, and so PD theory from well over 100 years ago gives you this smooth. I think it's over 100 years. For randomly switched ODEs, you can write down the PDE, but now it becomes a system of first order hyperbolic PDEs. So the PD theory isn't going to give you some nice regularity results in the same way. So that approach isn't really going to work. Now for degenerate diffusions, obviously there's some classical stuff from Horn-Mander and there's some very general conditions. The spatial distribution, so you have what's called hyperellipticity, which is just this requirement, so that L star u equals f, and f is c infinity, then u is c infinity. So if you plug f equals 0 in here, then that's the equation for spatial distribution, so it's hyperelliptic, then it's smooth. And this is stronger because the classes of these things are larger. And so for diffusions, you can show the very general results that it's hyperelliptic and therefore that's smooth spatial distribution. But for here, it's not going to be hyperelliptic, and therefore proving it by way of hyperellipticity is not going to get you there. So the sort of approaches from the diffusion case just kind of break down here. And so this is just a breakdown of the basic main difference. And so what we're trying to do is we're going to try and find some conditions giving you smoothness and safety distribution, or CK for large K, but with a different approach. Okay, so a bit of background material about what's already known. So in D equals 1, it's actually kind of well understood. There's a paper from actually Tobias and Yuri Bactin and Jonathan Mattingly from about 8-9 years ago now. And in dealing with the D equals 1 case. But here you notice that in D equals 1, it's not like PDEs, ODEs, or integral equations. And so somehow this analytic properties are going to be very different than when you have more than one dimension. But here they showed that when the density is infinite, and showed that when it's finite, then it's smooth. It's not clear from the outset you should expect the same qualitative properties, because okay, so first order PDEs and first order ODEs are different. In general, like if you write a simple first order ODE, you can have smooth solutions, whereas in, say, 2 dimensions, it can be often no. And also in more than 1 dimension, you can have complicated dynamical systems. So remember, we're driving it according to these vector fields. If those vector fields have complicated dynamical system properties, maybe some complicated attractor or something, that might have an effect on the stated density of the switch system. And obviously this phenomenon isn't possible in 1 dimension. Okay. And so that's what's in 1 dimension it's known. In 2 dimensions there's a couple of results, again by the same people. So the first one is that if you have a 2-dimensional torus, and you switch, and each of those toruses, you have 2 vector fields in the torus. You assume they're smooth, and each of them has a smooth invariant measure. And so then it showed that if you switch between these 2 ones, and the switch system has a smooth invariant measure. So we have that. And then there's a third result saying that in 2 dimensions, if you have 2 linear vector fields of a given certain form, you can characterize when it's bounded, when the safety density is bounded, or when it's unbounded. And as far as I know, dimension deal 3 is nothing. So that's kind of the state of what was previously done. Okay, so what are we going to do? So we're going to have arbitrary dimension, and we're going to have an arbitrary number of vector fields. We're going to basically describe qualitatively when the state distribution is smooth or when it's unbounded. So this isn't quantitative, it's going to be qualitative. We're going to establish that basically under Four-Mander type conditions on the vector fields, the safety density is CK whenever the switching rate between vector fields is sufficiently fast for any K. Now this isn't true for K equals infinity, because the notion of sufficiently fast is not uniform. So maybe I have to go a bit faster to get to C2, and I have to go a bit faster for C3, and even faster for C4, and so maybe I never reach C infinity, I don't know. That's the open whether you ever reach C infinity. But you can get a lot of regularity if you jump in quickly. And this sort of fast switching, it turns out, is necessary. So there's Four-Mander conditions and broad conditions on the vector fields, ensuring that the safety density is unbounded whenever the switching rate is slow. So if you switch slowly between the 2 vector fields, there's some conditions, but quite some broad conditions, but then if you switch slowly, you're guaranteed to be that the density becomes infinite, and therefore it can't be smooth. So, and the one result we have that applies to every switching rate is that the safety density is always relatively continuous. And so, in particular, if you have an infinite density, then the density has to go towards infinity as you get closer to the region within infinite density. So it's always relatively continuous. Yeah. Okay. So some basic assumptions. First of all, we're going to apply that there's some compact set such that none of the flows and none of the order differential equations exit the compact set. And so this is a set M. And so we're going to think of it as a process of M, lives in M, and it just makes all the analysis nicer. So we think of them as our space, and we're going to impose the same basic assumption that you use to establish existence and uniqueness. So there's some basic assumption that gives you that there is a spatial distribution that's unique, and obviously we're going to want to impose this. So, Hormander conditions. Maybe this is familiar to a lot of people here, but go over it. So we have the vector fields, and here V1 through Vn are the vector fields of our process. So they're the vector fields driving flows. And okay, so we have the definition of a lead bracket. So this is just this commutator thing. And so then we're going to inductively define these sets by just including more and more lead brackets. So you start off with V1 through Vn. So V1 through Vn are your vector fields of your flows. And then inductively you add all the lead brackets of them. So V1 is just by taking all pairs of lead brackets, and then V2 is lead brackets of lead brackets, and so forth. You just add more and more lead brackets. And finally you get V infinity, which is just taking as many lead brackets as you want. So, and then you can then define Vm of x to be a set of all such vector fields at the point x. So then the Vn infinity is the smallest of the algebra contained in V1 to Vn. So it's a classical definition. So we have three conditions. So the first one is Hormander's condition. This is the classical condition that which is that the span of V infinity at x is all of Rd for all x, which meaning that if you take as many lead brackets as you want, it has full rank. That's Hormander's condition. Then you have we can call it uniform ellipticity because if you actually write diffusions in this form, it's equivalent. Uniform ellipticity you can be thought of as just saying that span of V naught is the whole space for all x. So that's where you're not allowed to take lead brackets, you just start with your big lead vector fields. And then in between the two, we're going to have what we call a one Hormander condition, which is the span of V1, which means that you're only allowed to take one lead bracket. But you should notice that one lead bracket actually gives you quite a bit. So if I have n vector fields, then I have n choose 2 pairs, and so that's what n squared over 2. So now if you really from taking one lead bracket, that's giving me n squared over 2 vector fields. So it's actually giving me a lot just from the first lead bracket. And this one Hormander condition is going to be our main assumption of our main theorem. Okay, so we've got this notion of these conditions. I'll just state what the basic assumption is. The basic assumption is a Hormander's condition. So this is the condition that you have V infinity. That is. So Hormander's condition is satisfied at xr. The span of all the things with all the lead brackets is the full space at xr. And so we assume, so the basic assumption is that there's a point which you can reach by the vector fields from anywhere in M, and that the Hormander's condition is satisfied at that point. So it's quite general. I mean, I think you'd have to kind of be a bit inventive to think of something natural that doesn't satisfy this. But this is what we're going to call the basic assumption, which gives you this uniqueness of the spatial distribution. So that's the basic assumption. Okay, so back to the sort of qualitative picture. So we're jumping between the indices 1 to n, and each of these corresponds to vector fields. We're going to jump according to the vector matrix Q. And if you take a lambda constant, lambda greater than 0, the switching rate lambda Q represents scaling all the jump rates by a factor of lambda. So if I take 2Q, then I've doubled all the jump rates, and I'm switching between stuff twice the rate. If I take a half Q, then I'm halving all the jump rates. And so you can draw a picture. So if I have a slow jump rate, this is what it looks like. So I go blue for a long time, and I switch, and I go blue, and I switch. Medium jump rate, you go blue for a bit, and then you go red for a bit, and you go blue, red. And you're sort of jumping at sort of medium speed, and then a fast jump rate. You're kind of jumping between them very quickly. So go blue for not very long, red for not long, blue. This is clearly jumping very quickly. And so, okay, clearly for fixed vector fields, the spatial density is dependent on the jump rates. Because if I'm changing the jump rates, then I'm changing the process, and I'm changing the spatial distribution, it should clearly depend on the jump rates. So what we're going to do is, and we're going to write pi t for the spatial density for given rate matrix Q. So we fix the vector fields, and then think of the spatial distribution as a function of the rate matrix of the rates. And notice here that the basic assumptions giving the existence of the spatial distribution don't involve Q. So they guarantee the existence of uniques of Q for all Q. And so we're going to, the goal here is essentially to provide a qualitative description of how the smoothness of pi Q depends upon Q. Okay, so main theorem. So we're going to assume the basic assumptions. We assume that the one Hormandy condition is satisfied everywhere on n, which means that if I take, remember, that means if I take my vector fields and I take one in bracket, then at every point in space that spans all of RD, all of the space. And then what you then get is you get a function from spaces rate matrices to R plus, call this big lambda k, and you get this for all k, such that pi, that if we speed things up by a factor of lambda at least, big lambda k of q, then it's k times continuously differentiable. Then the spatial distribution is k times continuously differentiable. So in particular for those q's such that this function is less than 1, then it's continuously, it's ck. So what's this saying? This is saying that I can always speed things up enough to make it ck, and the amount I have to speed things up by is kind of locally bounded in Q. And so this gives us a notion of kind of fast jump rate. This is our notion of fast switching. And so when you have fast switching, then you have some nice regularity. Yeah, and so that's the main theorem. And so, okay, we're going to get sort of converse with slow switching. Okay, so we're going to think about pairs, gamma I. So gamma is a closed set in N. So it's a closed set in our space, our space. And I is just one of the states. So gamma cross I is a subset of our state space. And we're going to assume that every point in gamma satisfies the Hormandy condition. So this is just the Hormandy condition where you can take infinitely many brackets. And we're going to assume that the divergence of VI on gamma is uniformly negative. So the trace of dVi is bounded up below away from 0. And so particular this thing is supremum is negative. And you have 3 other kind of general conditions. And I should say it's quite typical for such a pair to exist. So I won't get into what the conditions are. So for instance, if you have attracting fixed points, this sort of thing works. Okay. So we'll note that the sum of j equal to I qij is how quickly you're jumping away from I. So it's the sum of all the jump rates away. So qij is how quickly you're jumping away from I. And so we assume that gamma I is a set satisfying these conditions, in the conditions on this slide. And so in particular, the supremum of the divergence is uniformly negative. And so because this supremum is negative, then this minus it is positive. And whenever the jump rate away from I is slower than this, then the spatial distribution, the spatial density is guaranteed to be infinite on the whole of your set. And it's in one dimension, because of the same you can do calculations for ODEs. And in one dimension, this is sharp. In one dimension, these gammas are just single isolated points, and you can calculate what it is, and it corresponds to the calculations here. And so what that means is somehow there's a balance between how quickly you're jumping away from I and how these sets are formed by gammas, because sort of they have the effect of squeezing mass. And somehow, if you're jumping away from I less than you're squeezing mass, then the squeezing mass wins out, and you get N plus infinity. And that's what this theorem is stating. This guarantees, therefore, that when you have slow switching under quite broad conditions, it can't be smooth because it has an infinite density. So, third theorem, which is lower semi-continuity. Recall what lower semi-continuity is, because I actually often have to Wikipedia which one's lower and which one's upper. But this basically is just saying that limit x goes to x0, f of x is at least f of x0. Okay, so basically, heuristically, it just means that f can only jump downwards, so it can't jump upwards. And so we're going to assume the basic assumptions. So this is the assumptions that guarantee that sort of standard that guarantee that the spatial distribution actually exists and is unique. And okay, so this, if you recall, means that the Hallman condition is satisfied at a certain point. And so, if those conditions are satisfied, then necessarily for any ray matrix Q, okay, reducible, then the spatial distribution is lower semi-continuous. The spatial density is lower semi-continuous. So under the same conditions guaranteeing the existence and uniqueness of the spatial distribution, it's also lower semi-continuous. Also has a lower semi-continuous density. And so in particular, from the previous theorem, if the spatial distribution density is infinite on this set, then as you approach the set, your density approaches infinity. So you can't have like isolated infinity, this can't happen. Yeah. And okay, so we've got some theorems here, so we'll take an example. So in this, so as I referenced earlier, Malwood poses essentially the question of what can we say about the smoothness of the spatial density. And he's going to he gives this sort of example where of a pair of linear systems, and he says that essentially, due to precise estimates from the one-dimensional case for these pair of linear systems, whenever the density at the origin, i.e. 0, is sufficiently small, Q12 is sufficiently small. So let's just apply our theory and see what happens to this system. So we have A is this matrix, E0 is here. The two vector fields of these two linear vector fields, B1 equals AX and B2 equals AX minus Z0. Okay, then you can just compute the Lie bracket, right? So this is linear vector fields, this is straightforward. And it's 0 minus 2. And you can just check that B1, B2, and 0 minus 2 always have span R squared. So that's done. So it's one Hallman condition satisfied, therefore Hallman is satisfied everywhere, it's done. So the conditions work. So what that means, first of all, here for this pair of linear vector fields, switching between them, if you switch fast enough, in the same sense as before, then your spatial density is CK whenever you're switching fast enough in the same motion as before, because it's just the same as the previous theorem. Okay, so at the origin, we have, okay, we can calculate dB1 is just of 0 is A, and the trace, so the trace of dB1, the divergence of B1, is just a trace of A, which is minus 2, by just taking the trace. Okay, so that means that the spatial density is indeed infinite at the origin whenever the 1 to 2 jump speed is at most 2. So if Q12 is at most 2, then yes, it's true actually that for Q12 at most 2, it's infinite. The spatial density is infinite at 0. And, okay, spatial density is lower than semi-continuous for any Q. So, okay, so for linear vector fields, and it seems this is quite simple. We can actually check this and apply the theorem. So, let's go for a summary. So previously, regularity of the spatial density is only really understood in one dimension. So there's a couple of systems where it's only 2D, but certainly not 3 or more dimensions. And so the goal here is to get a qualitative description for how the regularity depends on the spatial density, upon the jump effects in a kind of qualitative sense. So we have good smoothness, i.e. CK for large K, when you're jumping quickly, and the density often has singularity, i.e. so it's not smooth when the jump rate is slow, and it's always relatively continuous. And so this is in contrast obviously to diffusions for which the spatial density is C infinity under very general conditions. So where we can planning to go with this? We're going to recall that establishing the spatial density CK for fast jump rates required with one horn under condition, meaning you can only take one of these brackets, and there's a question about whether this can be extended to regular horn under. I think probably, but it's hard. I won't go into why it's hard, but it's hard. It seems hard. Okay, but then there's broadly, so the proof strategy here is sort of a bit different. So there's a question about whether we're going to extend the same proof strategy in different settings. So for instance, you might have a diffusion satisfying the elliptic horn under conditions only on an open set U. So on the open set U, horn member theorem gives you that it has the station density has to be smooth. That side of U doesn't say anything. And so then there's a question about what can we say about the regularity of the station density outside of U, and there's some idea that the proof strategy that we used in this case can be extended to there. Is the station density outside of U necessarily lower than continuous? If suppose that U, so now you're working with a diffusion that has a drift vector field. Suppose that U contains the global factor of the drift vector field. Does it then follow that the station density is CK whenever the noise is sufficiently small? Some of the arguments from this PD and P case would suggest that in that situation, yes, but okay, don't know that yet. And the third one is about what about the regularity of the station density random diffusion mechanisms? So can we get some theorem here? So this is sort of goals for the future. I think I'll just finish with a bit about the proof and the overall proof strategy. So I'll just start by saying the proof is probabilistic and it's not clear that there's an analytic proof. Maybe there is, but I mean I have no idea how to do that analytically. And it may be interesting if someone could do it analytically. Okay, so what's the idea? So first of all, we're going to consider a stopping time. And we're going to define Yn to be the discrete time markup chain on n plus 1 to n, whose time step is given by following your process up to the stopping time. So the idea is that I define a stopping time, and then I run the process up to the stopping time, and then I restart my stopping time clock, and I run it again, and I do that again. And this is a discrete time process, and it has a station distribution, and we're going to call omega station distribution. Okay, so we can also define a kernel, G, this thing, which G to define this kernel, you take your initial condition here, and you take the integral from 0 to e of your empirical measure up to ds, and you take expectation. So this is like expected sort of measure from 0 to the stopping time, and we can rely the station distribution pi to the station distribution of yn through this sort of formula. Okay, so we can somehow we have a spatial distribution yn, and we have a for the discretizing process, and we have a spatial distribution for our original xp, and somehow we want to relate the two spatial distributions. Okay, so the idea was to construct the stopping time such that omega necessarily has a smooth density. So omega, we're going to script the definition of, so we're going to construct the tau such that this is all the way C infinity. And then we want to do at the same time have it so that G maps C infinity densities to CK density whenever the jump rate is sufficiently fast. So if this is in C infinity and this maps C infinity to CK, then pi has to be CK. And so that's going to be the strategy. And the proof of the other two theorems is sort of similar ideas, but in different ways. Okay, so we're going to define the time step of yn is given by following x to it up to the stopping time. We want yn to have a smooth station density. So we'll recall, and this is I think, classical, that if mu has a smooth compactness toward density, and f is a smooth submersion, then the push forward f of mu on the left is also C infinity. Okay, if you want to C infinity, you have to have something on the tail, but generally C infinity works. And so you leverage this idea to construct the stopping time, guaranteeing that omega has a C infinity density. So the idea is you construct the stopping time such that your time step can be thought of as a push forward of smooth measure under the smooth subversion. And that guarantees that your stopping station density, omega, is always smooth. So that gives you the first step. Okay. Now the second step. The kernel G is defined by this expectation, right? So we recall this, G of xi equals expected value from 0 to tau of your empirical measure. And we're going to use basic analysis to obtain constants such that you have this. You have to construct the stopping time in the right way, but essentially yes, that you can make it so that CK norm of mu G is at most this expectation of e to the AK tau. So somehow what that's saying is, if you break down what's the important thing here, the important thing here is the stopping time, e to the stopping time. If the stopping time is long, then this expectation is infinite, and therefore this doesn't say anything. If the stopping time happens quickly, then this expectation is finite, and therefore this being finite implies that this is finite. Right? So that's the basic idea. So G maps the infinity densities to CK densities whenever this expectation is always finite. And that's the point, right? And there's a bit of analysis, but it's not hard analysis to do to get this. And so then the stopping time tau is constructed so that it corresponds to your states, IT, things 1 to n, following a certain sequence of states. And so the idea is that when you follow the chosen sequence of states, then the stopping time has the right properties. And the probability this happens in a given time converges to 1 as you make it faster and faster because of the infinite monkey theorem. So remember this theorem that if you get a monkey and you make it type whatever it wants arbitrarily quickly, then every sequence has to arise, right? So making that your monkey type faster means that your sequence of states has to have probability arriving close and close to 1 in any given time. And what that means is that this expectation is finite whenever your monkey is typing quickly enough. And since that's finite, then G maps C infinity densities to CK densities whenever the jump rate is fast. Okay? Big picture then. So we've related, the idea is then to construct some take stopping time, use that to construct some different station distribution, relate your original station distribution to this new one, according to this relationship, and then to have constructed stopping time tau such that 1, omega always has C infinity densities, which is done, and 2, G maps C infinity densities to CK densities under your desired conditions here, whenever the jump rate is quick. And once you've done that, you can conclude that your original station density has to have the pi, your original thing you're interested in, has a CK density whenever the jump rates are fast. And you can run a similar game of, if you're looking for different properties of saying, well, when does omega have this property, when does G map that to some other property, and therefore obtain properties of the station distribution. And so, for instance, to get infinite densities, you want to know, well, when does omega have a positive density, when does G map positive densities to infinite densities on the set, and the same trick works in the same way. And so obviously, I guess the future goal is to sort of extend this strategy to other settings and try to get some results, some qualitative understanding of station densities when we don't have hyperplicity. And I think that's maybe I'm a little bit ahead actually, but that's.
So you probably already knew that we had technical problems, so you sped up a little bit, and we are on time again. So, but we have time for questions. David, wanted to start?
Yes, so thank you for a really stimulating talk. Your talk reminds me of how much easier things get when you start with the distribution you're trying to get to, and rather than starting with the process and trying to understand the distribution. That raises a couple of questions for me. So these piecewise deterministic Monte Carlo methods are basically this sort of process, but where you, right, where the switching rate depends on the location. And so one thing I'm wondering is, do you know anything about that sort of setting? But also related to that, you have a set of vector fields, and you choose a switching rate. Do you know anything about and choose this different switching rates for the same vector fields give you different stationary distributions. So do you know anything about sort of the set of stationary distributions that you could get with a given set of vector fields by adjusting the switching rates in different ways?
Yeah, so I'll start off with the first one, which is something I've been thinking about. It seems that first of all, I think low semi-continuous, the same proof works. So it's always going to be low semi-continuous if you have switching. The question is about the other two properties, which are a bit harder. The issue here is getting this property mu g ck and estimating the ck norm when you have a varying switching rate can be difficult, and getting a nice handle of that is somehow it's the hard thing, and trying to come up with a notion of stopping time which gives you some analogue of this seems to be the obstacle there. So somehow if it doesn't vary much, then maybe you can get it, but trying to work out what's the right way of constructing stopping time so I can get an analogue of this. And so far, when I've thought about it, it's a main obstacle to trying to extend to varying time switching rates. But low semi-continuity, I think, works fine. Because low semi-continuity is just there using factors. An increasing sequence of continuous functions is low semi-continuous, so you can cut stuff off, have it continuous, and then just take a monotone limit, and that gets you low semi-continuity. And the second question was, do I know anything about the set of stationary distributions when you vary Q? No, not really. I mean, you know that they're all, assuming everything's always irreducible, the rate nature is always irreducible, then they're going to have full support, and I guess they're always going to be low semi-continuous, but that's all I can say. So I don't have anything better than that.
Okay, thank you. Further questions? Yes, please.
So omega is the distribution where with which you restart the process.
Yes, so you try to measure the stopping time, and so I run until the stopping time, then I restart my stopping time clock, and I run it again. That's a discrete time process, and omega is a stationary distribution of that discrete time process.
So then the questions, maybe there are two questions. To understand the properties, the smoothing properties of the green operator, and the second maybe to solve this equation which is not linear, it's somehow strange. In omega, given pi, you want to solve it for omega. Can you comment on that?
So given pi, you want to
calculate the admissible omegas, maybe there are more than one.
Yeah, so we don't really calculate omega per se, you just get some qualitative properties. Omega, it's generally quite easy to make it have nice properties because of one way to think of it is, suppose I have three directions, it's say R3, and I run a bit of time in this direction, a bit of time in that direction, a bit of time in that direction. So a bit in the x-axis, a bit in the y-axis, a bit in the z-axis. And I'm running Poisson time, Poisson has a smooth density. And now if I stop, if my stopping time is the time after which I've run in all three directions, then omega, the position of your step, is going to be the push forward of, Lebesgue plus Lebesgue plus Lebesgue, or something, the Poisson density plus Poisson density plus Poisson density, under this kind of smooth map. And so that's how you kind of get properties of omega. We never really calculate it explicitly beyond that, it's just, it has these properties and these conditions. Yeah, maybe it would be hard to get a sort of strong feel on omega. Yeah, and also often I will say that because of the way it's constructed, omega often doesn't have full support. So you'll define a stopping time so that the stopping time will correspond to a nice set, when ringing of a nice set, which means that omega can only be supported in the nice set. that somehow you that spreads around with the green kernel.
And you want to avoid the shape, probably the boundary. So
Yeah. So for instance, I mean, I didn't really say it here, but you don't actually require format on all of that M. You only require it on the attractor of the average vector field. Because if you're coming quickly, then you're going to, like, with large probability, go towards the attractor, and then omega is going to be supported on the attractor when this is sort of the nice stuff happens. It might be that bad stuff, like, you might have an area of space where there's no Allmander condition, so that's a bad place, and you want to construct how to avoid that bad place, and omega is not going to be supported on the bad place. Yeah, I hope that answers the question.
Okay, further questions? I have one. So you're working with one condition. I think it's getting easier and more explicit or more quantitative if you work with uniform ellipticity, so to say.
Yes. So I mean, there's one question that you might ask is, okay, so for slow switching you have a quantitative bound.
Yeah.
For the fast switching, we don't.
Yes.
Uniform ellipticity, and if you have not just uniform ellipticity, some estimate in some sense, then I think you can get some. You could get some quantitative bounds in the fast switching, and it does get easier with uniform ellipticity. But we haven't done that because we calculate would be 3-4 times and so on.
Okay. Further comments, questions? Otherwise, let's thank the speaker again. And if everything worked out, we have a coffee break and we meet again in half an hour, approximately. We're going to continue with Tobias Wood from University of Berlin, or the Free University of Berlin. We're going to speak about joint work with Kostya Kanin, Beatrice Lambeda, and Fedor Nazarov with the title Directed Polymers and the Stochastic Heat Equation. Thanks for coming from Berlin to Sofia.
Thank you, Martin, for the kind introduction, and thank you to the organizers for inviting me to this conference. Today I'll talk about a project that we've been working on for some time now. It started several years back at the University of Toronto with Kostya Kanin and Beatrice Navarro-Lameda, and then along the way Fedor Nazarov also joined us. The initial motivating question was to prove a suitable uniqueness result for global solutions to the stochastic heat equation. And let's see where we're at. We'll start with a very simple model, which is simply a simple symmetric random walk on the integer lattice, starting at some point x, and then you look at all the nearest neighbors of this point. So in this case, in the two-dimensional case, there are just these 4, and you choose one of these nearest neighbors, each one with the same probability, and then you jump to it. So in this case, from gamma 0, you would jump down to gamma 1. Again, you look at the 4 nearest neighbors, you pick one of them uniformly at random. In this case, you jump to the left, gamma 2, and so forth. And in this way, you obtain a path, which is marked in red here. And in our situation, we also imagine that there is a family of random variables, independent and identically distributed, which depend on the side of the lattice and also on the time that we consider. So we imagine that we're in discrete time. And then what happens is, starting from x, we just add up all these random variables that we encounter at the various sites. So in this way, we obtain the sum of random variables. On the next slide, this is made a bit more precise. Gamma is the discrete time symmetric random walk on ZD, where D can be any positive integer for starters. And we let the time run over all the integers. So we also want to be able to look at the random walk for negative times. We'll see later why this is important. Then the Xn are the IID random variables that I mentioned, and we assume that they have finite exponential moment, at least for beta sufficiently small. Now here it's important that we have two sources of randomness. On the one hand, we have the simple symmetric random walk, and on the other hand, we have the random environment, the random potential given by the x's. And to distinguish between them notation-wise, I use this kind of bracket to denote expected value with respect to the random potential. Now, so this is expected value with respect to the x's. And then we define an action associated to each sample path of the random walk simply by adding over the random variables that we encounter along the way. So that is this part. And maybe one more remark before we go on. Yeah. Where does the name directed polymers come from that we saw in the title? If you look at this red path of the random walk for finite time, this looks a bit like a polymer. So it's something connected, it bends and it folds on itself potentially. And this is maybe roughly what one would imagine a polymer in physics to look like. So this is where the name comes from. Okay. A bit more notation. This is now expected value with respect to the random walk, EXSYT, where we condition on the random walk being at x at time s and being at y at time t. So imagine that s is less than t, the random walk starts at x at time s, and then we follow its evolution up to time t, where it's supposed to end up at y. And q, y minus x, t minus s, this is simply the transition probability for the random walk. Okay. Beta, this was a parameter we had encountered before, so we want the exponential moment of the random variables constituting the random potential to be finite if beta is sufficiently small. And the C beta was simply this exponential moment. And then we define what's called a point-to-point partition function, point-to-point, because we fix both the starting point and the end point in this way. Using the Gibson formalism, we take expected value with respect to all the realizations of the random walk that go from x to y. And here we have exponential beta times the action. And you see that beta determines the strength by which this so-called partition function depends on the realization of the random walk. For example, if beta was equal to 0, that's something we don't assume, but imagine just for a second it was equal to 0, you would have 1 here, so you would always be equal to 1 no matter which realization of the random walk you look at. But if beta is a very large number, then this expected value depends strongly on the potential. In fact, I think I said this wrong now. Depends strongly on the potential, and in this way, beta determines the dependence on the realization of the potential. I think I said the random walk, but should have said on the potential. And here we have the transition probability, and this term here is a normalizing factor. Right? And now we also define the point-to-line partition function, where we only fix the starting point but leave the endpoint open. And here we just add over all possible endpoints. We're summing these point-to-point partition functions. Similarly, if we want to fix the endpoint and leave the starting point open, we just sum over all possible starting points. Okay? And then it's not hard to see, or in some sense the C beta is chosen in such a way that if we take expected value with respect to the random potential for a fixed realization of the random walk, and then multiply by this term, this is always equal to 1. And then using Fubini, you can show that this implies that the expected value of the point-to-line partition function, which is a random object with respect to the random potential. So now if we average over the potential, this is always equal to 1. So in this sense, the C beta is a normalizing factor. And now we start looking at a situation where we want the dimension to be at least equal to 3. And that's the following. So we consider alpha d, which is defined as this double sum over squares of the transition probabilities. And we also define lambda in this way. And this actually comes from the second moment of a centered and normalized version of the first exponential moment for the random potential. This is in some sense something that appears in the proof later on of the statement we're about to see. And now, since we know that the transition probability for the simple symmetric random walk can be bounded by a constant times n to the minus d over 2, we in fact have the following estimate for this quantity alpha d. We just estimate one of these two factors by this n to the minus d over 2, then we can pull this in front of this sum. And the second sum is just equal to 1, right? So then, in this case, you obtain this series which converges for d greater than or equal to 3. So that's why it's important to assume now in what follows that the dimension is at least 3. And then C9 showed in 1995 the following result. In dimension 3 or higher, for beta so small that the product of alpha d and lambda is less than 1, one has that the point-to-line partition function converges in the sense of L2 to a limiting partition function as we let s tend to minus infinity. And he also showed that this limiting random variable is strictly positive. Right? So from now on, when we talk about a limiting partition function, we'll mean either z minus infinity yt, or the limit in the other sense, that would be z xs infinity when we're going forward in time. And to show this, C9 used a clever way to represent the point-to-line partition function, and then exploited an orthogonality structure, which is inherent in this representation. And this is then also how these lambdas appear, how the lambdas come up in the calculation. As a corollary, once we have L2 convergence, we also have convergence almost surely. This follows simply from the fact that this sequence of partition functions is a martingale. This is not hard to see. This was, for example, pointed out by Erwin Bolthausen in a paper from 1989 for a similar model where he considered bounded noise, so a bounded random potential. But the proof just works the same way, and it was not the main point of this article. This also gives us almost sure convergence. And now there's an important dichotomy. This was already a little bit implied by what I've said about this dimension d having to be greater than or equal to 3 between what's called weak disorder and strong disorder. Strong disorder means that in the limit, as z goes to minus infinity, this limiting partition function tends to 0, almost surely. And weak disorder, this was the case that we've been looking at, this means that the limit is positive, almost surely. This was implied in particular by C9's result. And in dimensions 1 and 2, we always have strong disorder. This is always this case right here, no matter whether beta is large or small. So in the high and low temperature regime, there's strong disorder. And in dimensions 3 or higher, it depends on beta. There's a phase transition. If beta is sufficiently small, then we have what's called weak disorder. And if beta is large, we're still in a situation of strong disorder as in dimension 1 or 2. So as beta gets smaller and smaller, as beta decreases to 0, there's a transition from strong to weak disorder. In the regime of weak disorder, what is typical, what one can show, is that the so-called polymer measures behave diffusively. By polymer measures, we mean, simply the ratio of the point-to-point partition function, where x and y are fixed, and on the other hand, the point-to-line partition function. And it's diffusive in the sense of weak convergence. So here we're assuming that f is some test function, continuous and bounded. And we see that we get convergence, weak convergence, to the multivariate normal distribution for not exactly the polymer measures pi s, but here you see that you have to scale them appropriately. But then indeed, for almost every realization of the random potential, you get this kind of convergence here. Because this, as another remark, this measure is a random probability measure because it depends on the realization of the random potential on these random variables. This type of diffusive behavior was shown by several people, not just Sinai in his 1995 paper, but for similar but related models, first by Imbri and Spencer, and then also by Bolthausen in his 1989 paper. This was actually the main point of that article. What is new in Sinai's approach, other than that he allows for a larger class of random potentials that only need to satisfy this finite exponential moment condition, is that in his proof technique, he uses what one could call a factorization formula for the point-to-point partition function. And the idea is that he says, well, if time is sufficiently large, if I look at my random walk over a sufficiently large time interval, then I can almost write the point-to-point partition function as the product of two point-to-line partition functions, and then the transition probability of going from one side to the other. Here is a picture that tries to explain the philosophy. Let's first have a look at these two red curves. So we fix a starting point x at time 0 and an endpoint y at time t. And you should imagine that t is quite large. So you give yourself a lot of time to reach y at this particular time t. And now you're interested in the quantity z x naught yt, the point-to-point partition function related to the random walk going from x to y. And these red two curves represent then this point-to-point partition function. So they look at the potential paths. You could imagine that between these two curves are all the possible paths that the random walk could take to reach the site at time t. And now we say this quantity, this point-to-point partition function, can be thought of as follows. If time-wise we're still close to 0, then there's a part to this point-to-point partition function, a factor if you want to, that should be quite similar to the situation where we don't fix the endpoint, where we leave the endpoint open. So for small time somehow, the red curve should be close to these two black curves that represent the situation where we do not require the point y to be reached at time t. We just start at x at time 0 and then we move around. Right? A similar remark applies to the endpoint. So if we want to know what we can say about times that are close to t, then the part of this point-to-point partition function that corresponds to such an interval should be close to these two green curves where we don't fix the starting point, where we don't fix x. And then what remains is all the times between this time close to 0 and this time close to t. And when we're in this intermediate regime, you can think of strong averaging happening, and there somehow a good approximation to what's happening is just the transition probability for the random walk, where we don't see so much the effect of the random potential, we don't see so much the effect of the random environment. Okay? And mathematically, this is made precise on the following slide. This first formula, you can think of this just as a definition of the error term delta. There's nothing happening here yet. This is just, you can always write down such a statement and then say that delta is defined by this formula. But now what we want to say is that this delta gets small somehow. That as the difference between s and t tends to infinity, delta tends to 0 in some suitable sense. And what Sinai showed in his 95 paper is the following in what one could call the diffusive regime. So for points x and y, whose distance is on the order of time scaled raised to the power 1/2, that's the typical diffusion scale. The first moment, or the L1 norm, with respect to the random potential for this error term tends to 0 uniformly. And this was enough for what he tried to do. So in order to show in order to show this type of convergence statement here, this is enough and this works well. For what we wanted to do, it was somehow important to extend the factorization beyond the diffusive regime. And this is where Fedor-Nazarov helped us crucially, some of the technical aspects involved there. And in the end, we were able to extend it to what one could call the sub-ballistic regime. So here we have a parameter sigma, which can be arbitrarily close to 1. This is important. And then for any sigma, there exists a theta, and we get this rate of convergence then. It doesn't matter how big or small theta is, it just matters that we have this power law in front. And so these are the two main differences, that we get some rate of convergence here, and that we can extend the factorization formula to the sub-ballistic regime for points that are now potentially quite far apart. This is not a trivial extension, because you have to work with very careful estimates on ratios of random walk probabilities, where starting and endpoint are quite far away from each other. We can imagine that this is known still, but we are not able to locate it in the literature. Fedor-Nazarov was able to come up rather quickly with a proof of this statement, so it is somehow at least implicitly known, these ratios for transition probabilities, but we just could not locate them. Okay. And now we'll see why we're interested in obtaining such a factorization formula. Why for us the diffusive regime was not enough and we actually needed this kind of statement. I think it's also a bit interesting mathematically in its own right, and it could potentially have other applications than the one that we're working with. But what we're interested in is, in particular, the stochastic heat equation. So now we shift gears a little bit. Up to this point, we've assumed that time was discrete. And now we let time be continuous, so that we can look at an SPDE. But we still assume that space is discrete. So we want to look at what we could call the semi-discrete stochastic heat equation. The space is still the integer lattice ZD, and time now takes values in R. And then here we have the graph Laplacian for ZD, just defined in this way. And beta plays the same role as before. We assume that beta is small. And now the random potential, the random environment, is given by white noises. Independent white noises that are indexed by time. running over R, so we also want time to be able to go to minus infinity, and also indexed by space, y. And then we have this initial condition, so we look at the corresponding Cauchy problem at some given time s, and we assume that f is a strictly positive function on the integer lattice. This is just a picture to see the idea. We start at time s, there's this function f that we're given, our initial data, and then if we want to know what the solution looks like at time t, at a point y, we have to take into account somehow what happened up to time s. And this picture and this idea relates very much to the Feynman-Katz formula. And through the kind of Feynman-Katz formula, we can make a connection then to directed polymers. And in particular to the first part of this talk. Now we assume that we're given a continuous time simple symmetric random walk. So essentially it's very similar to the first random walk we saw, just that now we wait at a site for an exponential time, and then we jump to one of the nearest neighbors, again chosen uniformly at random. There again we start an independent exponential clock, we jump, and so forth. And we define a random action assigned to a path of this random walk in this way. It's a similar idea as before, we just have to make some adaptations now for the continuous time setting. A priori, we don't know how often we jump from time s to t, so some of the number of jumps nst needs to appear in the formula, and then the times at which we jump, the sites to which we jump also, and the random variables will now be increments of the Brownian motions at these sites. No? They could be positive or negative, we add them up. Similar idea to the discrete time case. And then we can define, again, partition functions, point-to-point and point-to-line partition functions, where the idea, again, is similar. This is now the transition probability for the continuous time random walk, and this factor here normalizes things in the same way as in the discrete time case. And then what we can use is this result by René Carmona and Stas Monchanov, published in an AMS monograph in '94, which says that under some regularity assumptions, in particular at most exponential growth for the initial data, we can write the solution to the Cauchy problem right here, interpreted in the Ito sense, simply as follows. Oops, no. So we sum over all possible points, and then we have our initial datum at x, and we multiply by the point-to-point partition function. This is in fact the unique solution to the Cauchy problem. Okay. And now we want to use this formula to point out a particular global solution, a solution which is defined for all times. First of all, we use the same definition as a discrete time for the point-to-line partition function, where we leave the starting point open. And then we have a formula which you can think of as a Chapman-Kolmogorov formula. You start at time r at some point, and you want to reach y at time t. And then you tell yourself, well, I could just fix some time s between r and t. I could see where I end up at time x. And then I could have this relation here. All right, so I go from r to some point x at time s, and then I go from x to the point y at time t. And in this formula, what you want to do next is you want to let r tend to minus infinity, so that you see that it also holds for the limiting partition functions. Now this works, you can do this. And in this way, you obtain this relation right here. And this is then indeed, by Feynman-Katz, a global solution to the stochastic heat equation, where you should think of this expression now as the initial data at time s, right? And then you can say that indeed for any time t, this expression, because of this formula, solves the semi-discrete stochastic heat equation that we saw before. And it's not just any particular global solution, it's in some sense a very special global solution because it attracts other nearby solutions. And this is, you could say, the main theorem that we were able to prove in this setting. Right here. Let's make precise what do we need in order for this statement. We consider initial data that grows sub-exponentially but also decays sub-exponentially. So in particular, we assume that these two inequalities hold for f of x for some constants c and epsilon. Let's say we fix these two constants. And then the statement we're able to prove is the following. If beta is sufficiently small, uniformly over initial data in this class of functions, you obtain that the ratio of this particular global solution, where here you pick any point y, and here, let's say you fix y equals 0. So you need to have this sort of division, otherwise you could not expect uniqueness. There's no hope to get this kind of unique result if you don't normalize in this way. And then you look at the difference between this and what happens if you solve your Cauchy problem for this given initial data f, starting, let's say, at time 0. And then as t tends to infinity, these two quantities get closer and closer and tend to 0 in probability. There is a chance that this might also in a stronger sense than just in probability, but this is what we're able to show. And in fact, this already, we think, this is sort of the missing step in our program, we think that this then gives you uniqueness of the global solution within a class of stationary solutions. If there's time, I'll talk about this towards the end of this talk. Okay? This is the statement. Here, this is represented graphically again. The green curves correspond to the particular global solution, to this z minus infinity yt. And the red curves correspond to the solution of the Cauchy problem, where at time 0, we prescribe initial data f. Right? And then we say that as we let time tend to infinity, as we move upwards here, somehow the two get closer together. We have this attraction result in the forward sense. Okay. Some remarks about this statement, because we've made several assumptions here, and so I want to talk a little bit about which of these assumptions are essential for what we want to do, and which assumptions can perhaps be relaxed. What is important is that we're in dimension 3 or higher, and that beta is small. So in other words, that we're in the regime of weak disorder. You can see this simply because here we're looking at ratios of these partition functions, and in the regime of strong disorder, these limiting partition functions would be 0. This wouldn't make much sense. Okay. This is crucial. We're looking at the situation of discrete space, and this is a bit unnatural, one might argue, because we're interested in the heat equation in an SPDE, so technically space should be, or morally space should be continuous. This raises some technical difficulties that presumably can be overcome. Here one should cite an important article by Yuli Kiefer from '97, who does consider continuous space, and who also shows the factorization formula, SCNI, in the diffusive or subdiffusive regime. And he has some sort of uniqueness statement, but within a smaller class of functions, so it's a bit weaker, his uniqueness statement. But his approach, his paper, gives hope that it's possible to relax this discrete space assumption. And then another question is, what about the potential? Here we're assuming that the potential is given by Brownian motions, could we have some other process? Could the potential come from something else? We're also assuming that the Brownian motions are independent for different sides. Now, one natural idea, one natural assumption would be that there is some short-range dependence. This should still work, even though we haven't thought about this more deeply. And another question would be, how important is it that we have a Gaussian process? Could this also work for other kinds of processes? If you think of Sinai, he doesn't just consider normal random variables. The only assumption he makes about the random potential is this finite exponential moment. Can we have something similar in our situation as well? And the answer here is maybe. It does seem possible a priori, so it's not such a clear no as for the weak, strong disorder question. But one important caveat is that what we use crucially in our proof is sort of precise lower estimates on the limiting partition function. And to obtain these lower bounds, we use Talagrand's approach, in particular the Gaussian concentration inequality. So here Gaussianity is important. Gaussianity does play a role. Maybe towards the end of the talk, let's have a look at the proof. This is the proof sketch, but it still gives you an idea of how this is shown. Many of these steps require rather detailed calculations, at least the way we did them, detailed justifications, but still I think the main idea is conveyed without taking away anything from rigor. So let's assume that we fix C and epsilon and a function f in this class of sub-exponentially growing and sub-exponentially decaying functions. We also fix a sigma, and here we should think back now to the factorization formula, where we said for any sigma, no matter how close to 1, we have this factorization formula. The error term is small. So this is where we need it actually. We need to be able to choose sigma greater than 1 plus epsilon to the minus 1 half. Okay? And then we start by just writing down the definition of this solution, UFYT. By finding cuts, we can write this as the sum of f of x and the point-to-point partition function, and we split the sum in the first step. We consider those points that are in the regime of t to the power sigma and those points that are outside of this regime. Right? And then we look at the first term and we split the first term again, having in mind exactly the factorization formula. So along the lines of the factorization formula, what we want to say is that this partition function here can be approximated well by the transition probability times the product of the limiting partition functions. And then here we need the error term also multiplied by the transition probability. This is an important step where something is swept under the rug now. Before I stated the factorization formula in the situation of discrete time, a similar formula, essentially the same statement, also holds in continuous time. At least the way we prove it, this is not a trivial corollary of the previous result. It uses the same ideas, but due to the fact that in continuous time we can have arbitrarily many jumps in a given time interval, things get much more technical, much more complicated, but still you have the same result, you have the same factorization formula. And now what we want to say is that this red term here is the dominant one. The other two terms are small in comparison to this term, in the sense that if you divide each one of these two terms by the red one, then the resulting quotient will go to 0 in probability as t goes to infinity. This is more or less clear for the term right here based on the factorization formula. For this other term, for x outside of this regime, what we can say is, first of all, since f has sub-exponential growth, we can bound this expression in this way. And then we just take expected value with respect to the random potential. And if we do this, well, this term doesn't depend at all on the random potential. It's only this partition function that does. And then you get just the transition probability here. And this is a simple analysis estimate. You can show that this expression indeed tends to 0 because we assumed before that sigma is greater than 1 plus epsilon raised to the power minus 1. And then, so what this implies already, let's go back to this slide. What this implies already is that the second and third term are small. But in principle, the first term could be small as well. So this doesn't give us yet that the second and third term are negligible in comparison to the first one. Right? And to see that the first term doesn't become too small, we need to be able to find lower bounds on these limiting partition functions. And fortunately for us, this was already done, not quite in the same setting, but in a similar setting that let us adapt essentially the proofs. It's written down in a paper by Philip Carmona and Julian Hu from 2002, and they use the method of Talagrand. And even though he may not have published this proof, but I think they also acknowledge that the proof goes back to him in this particular setting. So he shows that if beta is sufficiently small, we can estimate the probability that this limiting partition function becomes very small in this way, by exponential minus u squared divided by c. And as a corollary, this gives us then, after some calculation, that with high probability, the product of these two limiting partition functions is bounded from below by a quantity that does go to 0 as t tends to infinity, but at a rate that we can control, at this power rate. And now if you think back, let's maybe go all the way back to the factorization formula. There we have this rate of convergence, so this is needed at this point. And in this way, we can indeed show that the red term is the dominant one. And then, roughly speaking, what we can do is we can say that this ratio that we're interested in and we want to show, remember that this ratio is close to the corresponding ratio for the limiting partition functions, to this ratio. We can write this just as the ratio of the red terms, of the dominant ones. And then we're almost there. We just need to say that the ratio of these two sums is close to 1. But these two sums are almost the same. The only difference lies in the transition probabilities. And so all we need to argue is that this ratio of transition probabilities is close to 1 uniformly in X. And this is again an analysis then. So in this way, we can show this attraction result. And now we'll switch gears one more time. So skip the slide. Yes, skip the slide. Now we move towards a setting that is maybe more reminiscent of random dynamical systems. So now we start to care about the exact realization of the noise, of the random potential. So let's be a bit more precise now. We give ourselves a sample space omega, which is simply the z default product of the Wiener space. So we look at continuous functions on the reals, which are equal to 0 at the origin. Right? So that we can model our two-sided Wiener processes. Q is the two-sided Wiener measure on this space. And then we introduce the notion of a global stationary solution to the stochastic heat equation. And this is a function z, with the following properties. There exists a measurable set omega prime, a full measure, which is shift invariant. And by the Wiener shift, we just mean the regular left shift, but where we also make sure that the resulting trajectory still passes through the origin at time 0. Right? So it's shift invariant, and then for this set, omega prime, we want, first of all, that Z is a solution. This is what this first statement says. If you think back to the Carmona-Molchan result, to the final cuts formula. And second of all, we want stationarity in time. We don't assume any stationarity in space, but we do assume that we have this kind of stationarity in time, that if you look at the solution at time t, with the noise realization omega, this corresponds to looking at the solution at time 0, where the noise is shifted by t. And then the missing ingredient, and what we would like to do, this is probably not hard, but when we had a proof of this, but then I think there is a gap, but I think it should not be too difficult to show this, is that the limiting partition function is not just a solution, but it's also a stationary global solution in this sense. What is a bit tricky there is to show the existence of the set omega prime, which is invariant under all time shifts. Now we have continuous time, so just as a reminder, this adds a bit to the difficulty, and then we want these two features to hold. So it essentially revolves around this, the difficulty we're experiencing. But assuming that this holds, so assuming that you can show that the limiting partition function is a global stationary solution, the following result would be true. Again, we're in this typical situation where the dimension is greater than or equal to 3, and where the inverse temperature is small. And then, given a global stationary solution, which has sub-exponential growth, this is what this condition here says, you can show that Q almost surely, the ratios actually coincide. The ratios for this particular global stationary solution and the ratio for the global stationary solution coming from the partition functions. So in this sense, we would have, in fact, uniqueness of the global stationary solution. Okay. And then one last slide, which goes a little bit deeper into the formalism and language of random dynamical systems. In fact, we can associate a co-cycle and then also a skew product to the situation we're interested in. We define L to be our state space. This is just the space of all sub-exponentially growing and decaying functions, where LCE is exactly as it was defined before. Here I've written down the definition again, but you can just refer back to the definition we saw earlier. And then we can indeed define the co-cycle phi t omega f just by assigning to every function f in the space L, to every noise realization omega, and to every time t, the following new function, which is still in L, where here we have just the ratio of solutions for the Cauchy problem. Right? This was just the UF that we defined before at y and t, and this is the UF at 0 and t. And then the skew product is defined in the usual way. And in fact, if we can show this statement, so this uniqueness result for the global stationary solution, then we can also prove a uniqueness result for the invariant measure of the skew product, theta t. And this would simply be integration over Q, so over the two-sided Wiener measure. And then here we just have delta distributions for these ratios that as we saw before, that would not depend on the choice of the particular global solution. So here you could just put the limiting partition function z minus infinity yt, z minus infinity 0t. And then to finish, maybe some concluding remarks. Another reason why it would be interesting to study the same problem in continuous space, other than from the fact that it's natural to study the stochastic heat equation in continuous space, is that then we could do something that Kiefer did in his paper. We could link our results to the stochastic Burgers equation and Hamilton-Jacobi equation via the Hopf-Kohl transform. The Hopf-Kohl transform relies on continuous space, and it's not quite clear what an analog of it would be in our discrete setting. And maybe one last comment. We're assuming throughout that the initial data has sub-exponential growth. So we do not quite allow it to grow exponentially. This should probably be doable though. One should probably be able to cover the situation where one can write the initial data as e to the, and then we have some linear function in x plus a function of sub-exponential growth. But then what one would have to do is one would have to consider random walks with a drift. So not just simple symmetric random walk, but a random walk where this linear function in x induces a drift in a certain direction. Thank you very much.
Many thanks for the talk. Tobias, any questions right now? I have one. I mean, it connects a little bit to the remark you just made. So in the beginning, you always work with a simple random walk. Mm-hmm. So how much changes if I just take an arbitrary one with second moments or something like that? So does it really rely on working with a simple random walk, or can you work more generally?
I think you can work more generally. We haven't thought about this in detail, but I think this can be done. We do rely on estimates for transition probability. For transition probabilities quite a bit, okay. But you can. These are also, let's say they're stable in some sense. So you can assume a little bit more. You could conceivably consider a broader class of random walks than just the simple symmetric random walk. But what you would still need is the kinds of estimates for the transition probabilities that we're exploiting.
Okay. And the transition between d equal 2 and d equal 3, is it just somehow the recurrent transition? Or
yeah, this is
the reason?
Yeah, this is essentially the reason, yes. Mm-hmm. And this is also, I mean, if you think back to one of the first slides where we looked at the quantity alpha d, yeah, okay. Where we saw that the series converges only if d is greater than or equal to 3. This is also related, of course, to the transients and recurrence question.
Okay, yeah.
I keep wondering about how important are cancellations. Maybe also tails. How do you address the tails? For instance, for the approximate factorization of this transition probability. Can you comment on that? I mean, cancellations of the potential, basically.
Yeah. They are important, and we do. So let's put it this way: if there were no cancellations, I wouldn't know how to prove the results. In this sense, we rely on them. There, of course, other mechanisms that also enter the proof, but cancellations are an important part of this. Yeah, they make the machinery work. Otherwise, I wouldn't know how to approach this problem. Maybe costly, but it is important.
Okay, last comments before lunch. None, then let's thank the speaker again.
So for the first talk, we'll have the pleasure to listen to Samuel Johnston from King's College from London. He'll be talking about the smallest and largest fragment in self-similar fragmentation process. So thank you for coming to talk.
Thank you very much, Ruben, for the introduction. Thank you for the organisers, Ladin, Bristow and Martin, for the opportunity to speak and the opportunity to make my first trip to Bulgaria. I tried my best to miss the flight yesterday. For some reason I thought it would be a good idea to go to London Luton Airport to get a 10:40 AM flight from London Stansted. But I managed to catch my flight there. So I'm Sam Johnston from King's College London. I'm going to be talking about self-similar fragmentation processes. This is joint work in a team of 5 with Piotr Zajewski, who's at Wrocław, Nina Gantat at Munich, Joshua Prochnow at Passau, and Dominic Schmidt at Bonn. So this talk is about fragmentation processes. Fragmentation processes are stochastic processes modelling the evolution of an object that breaks apart as time passes. So it's any sort of stochastic process where we have an initial object that's in a block of mass 1, and then as time passes, this block breaks apart. So you might think of a fragmented hard drive, or a star breaking up into pieces, or a bunch of rocks inside a cement mixer, or a bunch of onions on a chopping board. The fragmentation process is a stochastic process modelling one of these, some object that randomly breaks apart as time passes. The theory of fragmentation processes was initiated by Kolmogorov in the 1940s. Kolmogorov gave an answer involving branching random walks to a question that had been observed in science, namely that if you take a bunch of rocks and you try and break them down, say with a hammer or in a cement mixer, and you do this process for a while, and you look at the logarithms of the sizes of the blocks, they tend to follow, maybe surprisingly, a Gaussian distribution. Kolmogorov gave a mathematical explanation for this phenomenon involving branching random walks. It wasn't, however, until the noughties and 90s and noughties with Bertoine and also Garistiki that a real sort of general theory of fragmentation processes started to emerge. And this theory supposes that the process is a Markov process and that the fragments in the process behave independently. So the fragments have independent random lifetimes where the lifetime of the fragment depends on the mass of the fragment. And it's also assumed that when a fragment dies at the end of its lifetime, it breaks into some smaller fragments according to some scale invariant rule governed by a dislocation measure. So a fragment of size m might break up into some smaller fragments whose mass adds up to m, but in such a way that the ratio of the smaller fragments and their ratios compared to m don't necessarily depend on the size of m. So we have a scale invariant rule for how particles break apart at the end of their lifetimes. In fact, unlike in this picture here, the framework is more general than this. So a fragment at the end of its lifetime can break into infinitely many pieces, where these infinitely many pieces add up to the size of the parent fragment. And what's even more cool in the theory that was developed is that there's even a theory accounting for sort of continuously crumbling fragments in time. So it's not like the fragments have finite lifetimes and then at the end of their lifetime they break, but they're sort of continuously breaking as time passes. So if I start off with my initial fragment at time 1, and I look at a tiny amount into the future, it's already lost a tiny amount of its mass into some other fragments. And today we're going to be interested in self-similar fragmentation processes. So this means that the lifetimes of fragments are proportional to the power of the size of the fragment. So more specifically, a fragment of some size n breaks at a rate n to the alpha, where alpha is some index. And again, at the end of their lifetime, will supposedly break according to a scale invariant rule. Now, I want to argue, it's a bit of a joke, this slide, but it's also not a joke. I want to argue that the idea of a fragmentation process being self-similar, i.e. the idea that things break at a rate proportional to the power of their size, is actually maybe quite a natural physical idea. So you may have noticed, I hadn't noticed this until recently, but you may have noticed that when you're chopping pieces of onion or pieces of anything else on a chopping board, there's sort of a nice fact of life that as your knife comes down on the chopping board and more or less randomly hits pieces of onion, it's more likely to hit the big pieces than it is to hit the small pieces. So this means that when you're chopping onions, there's a sort of nice regularizing effect happening, where it's not like some pieces get too small and some pieces get too big, but the big pieces, their sizes sort of catches up with the smaller pieces. And it's even, I would argue, sensible to suggest that the way onions break apart is proportional to the cube root of their mass. So if you have an onion fragment of mass m, then the diameter of that fragment of onion is proportional to m to the third. So the probability that it gets hit by the cook's knife is proportional to m to the third. So onions on a chopping board are a self-similar fragmentation process with index alpha equals a third. So in general, be it onions or anything else, when something fragments and the index of fragmentation, the index of self-similarity is positive, the big fragments tend to catch up with the smaller fragments. The big fragments are more unstable, they're more likely to break, and they're more likely to become a similar size to the other fragments in the system. And when alpha is less than 0, however, the small fragments break more quickly than the big fragments. The small fragments are more unstable. Now, in the talk today, I'm going to be mainly interested in the alpha greater than 0 case, where the big fragments break more quickly. But for no other reason than because it's interesting, I thought we could take a very quick look at the alpha less than 0 case. So in self-similar fragmentation processes with alpha less than 0, as I said, the smaller fragments are more unstable than the larger fragments. And what happens in these processes is some small fragments start to emerge. Because they're small, they're unstable, they break even more quickly into smaller and smaller fragments, and there's sort of a runaway cascade of fragmentations. And what happens in these self-similar processes with negative indices is after a finite amount of time, so there's a sort of explosion where a positive proportion of your initial mass is contained in quote-unquote dust, which means that if you take a countable sum of masses of all the fragments in the system, it adds up to less than 1. And a bit later, more fragmentations happen, and the pieces get smaller and smaller, the fragmentation gets faster and faster of all of the fragments in the system, and after some later random finite time, there's a sort of final explosion where all of the initial mass is contained in dust. So by this I mean that there's no fragment of positive size after this random period of time. So that's self-similar fragmentation processes with negative exponent. But as I said, we'll be interested in self-similar fragmentation processes with a positive index today, where the large pieces break more quickly than the smaller pieces. And more specifically, we'll be interested in describing the sort of range of possible sizes of the fragments in such a system as time gets large. Now, there's a result on this front by Bertoine describing the largest fragment in such a system. So if you take one of these self-similar fragmentation processes, where a fragment of mass m breaks at a rate proportional to m to the alpha, and you look at the largest fragment in the system at a large time t, it turns out that up to a sort of rough order, the largest fragment in the system has a size that looks like e to the minus 1 over alpha log t. If you prefer, it means roughly speaking, the largest fragment has a size t to the minus 1 over alpha. Now, this result by Bertoine is for general self-similar fragmentation processes with a positive index. Today, actually, we'll be studying the simplest possible example of a self-similar fragmentation process with a positive index, where every particle, at the end of its lifetime, just splits into 2 particles. And we'll be interested in describing the largest and smallest fragmentation process. So we study what we call the Q process, the simplest example of one of these self-similar fragmentation processes. So in the Q process, you start with a single block of mass 1, and it has a standard exponential lifetime. And at the end of its lifetime, it breaks into 2 pieces of size 1/2. And then after that, all particles, all fragments in the system evolve according to the simple rule. Their lifetimes are exponential with rate mass to the power alpha. And at the end of their lifetime, they break into 2 equally sized pieces. So here's a simulation of one of these processes. And you'll see that as time passes, the fragments break into smaller pieces, and every fragment in the system has a size that's a negative integer power of q. Now the reason we call this a q process is because if we define the parameter q by 2 to the minus alpha, then a fragment whose mass is 2 to the minus n breaks at rate q to the n. So just packaging up what we've seen, the q process, which is the simplest example of a self-similar fragmentation process with positive index, evolves according to this rule. We start with a single fragment of mass 1, and more generally, a fragment of mass 2 to the minus n breaks at rate q to the n into 2 equally sized pieces. So returning to our goal of the talk, we have this Q process, this simple fragmentation process where pieces of mass break in half. And we would like to describe the smallest and largest fragment in this process as time passes. So since every fragment has a size,
So there is no dust in your model?
There's no dust, So since every fragment in the system has a mass of the form 2 to the minus n, where n is a non-negative integer, we can let 2 to the minus little n and 2 to the minus big N be the sizes of the largest and smallest fragment at time t. So this creates 2 increasing integer value stochastic processes that describe the range of sizes of the smallest and largest fragments in the system. So rephrasing our goal, we would like to understand these processes as time gets large. So there's a way of thinking about this process in terms of branch and Markov chain. So we start with a single particle at level 0 in this chain, and this particle has a standard exponential lifetime. And then at the end of its lifetime, it dies, and it is replaced by 2 children particles on level 1. And then a child particle on level 1, each of these kids has an exponential lifetime of rate q before dying and being replaced by 2 kids on level 2. More generally, one of these particles on level n has an exponential lifetime with rate q to the n before dying and being replaced by 2 child particles on the level above. When we say take a snapshot in time here, so I've chosen a time t here, I have 1 particle on level 1 and 2 particles on level 2. That's equivalent to our fragmentation process at that moment in time, having 1 particle of size of half and 2 particles of size a quarter. So this is kind of a convenient way of drawing our fragmentation process as time passes. Now when we zoom out on this drawing, we have these sort of branching Markov chains on all of these different levels. And since each chain splits into 2 as when it dies and gives birth to 2 particles on the level above, we have this sort of cloud of Markov chains evolving as time passes. And this cloud is contained between 2 integer stochastic processes, little n and big N of t, which govern the size of the smallest and largest fragment in the process. So we would like to kind of describe what this cloud looks like as time gets large. And before we do this, however, we want to get a very rough idea of how this cloud evolves. And a simple way of doing this is to just follow one of these chains forward in time at each split. What I mean by this is each time one of these chains splits and has 2 kids on the level above, we flip a coin and follow one of those kids at random. Another way of saying this is if we take our fragmentation process, it starts with a block of mass 1, which has a lifetime, and then at the end of its lifetime it splits into 2 blocks of size of half. We forget about one of those blocks and just follow one of the halves. Then we follow one of the quarters, and then we follow one of the eighths. So we can sort of follow a typical fragment in the system as time passes and get a rough idea of how the system evolves. It turns out that that procedure I just described of following one of the fragments, flipping a coin to follow one of the child fragments at each split, it turns out that if you let 2 to the minus xt be the size of the fragment you're following at time t, it turns out that this represents actually a size-biased fragment from all of the fragments there are at time t. i.e., if you have a bunch of fragments of different sizes at time t, and there's some fragment whose mass is 1/8, then you have a 1/8 probability of being following that fragment at time t out of all of the fragments. But anyway, more importantly, this path xt just gives us some sort of anchoring idea as to how this cloud evolves at time t. Because this path xt is a simple Markov chain that spends an exponential amount of time on the first level, exponential rate q on the second level, and exponential rate q to the n on the nth level, etc. This means that the exit time of the level n is roughly of the order q to the minus n, where q is less than 1. So the amount of time it's spending on level n is exponentially increasing in n. When you invert this relation between n and t, what you find is that the height of this Markov chain at time t, xt, is roughly kappa log t. So this means that, roughly speaking, the typical path looks like log t. So we just saw in the previous calculation that if you take the minus log base 2 size of a size bias fragment, it has roughly size kappa log t. And when you translate Bert-1's result about the largest fragment in self-similar fragmentation processes into our parameters, q, alpha, and kappa, it turns out that Bert-1's result also says that the minus log base 2 size of the largest fragment in the system is roughly kappa log t. So roughly speaking, this is indicating that at large times t, the largest fragments have size roughly 2 to the minus kappa log t. Okay, we now state our main result, and our main result says that, surprisingly enough, at large time t, you can pinpoint with very high accuracy the sizes of the smallest and largest fragment in the system. So here's just another definition of a reminder of what our stochastic process is. It's a really simple stochastic process where you start with a block of mass 1 and a block of mass 2 to the minus n breaks at rate q to the n. Turns out in this process, if you let 2 to the minus little m and 2 to the minus big M denote the largest and smallest fragments in the system, then with very high probability, little m of t, or 2 to the minus little m of t is the size of the largest fragment, so little m of t is very likely to be a specific integer near kappa log t minus log log t. And big M of t, which governs the size of the smallest fragment, is very likely to be a specific integer near kappa log t plus the square root log t term. So you're probably wondering what exactly I mean by specific integer. I'll be more specific. When t is large, then with very high probability, little m of t is likely to be this exact integer here, where this is the ceiling function of kappa log t minus log log t minus log gamma k. Gamma here is log 2, and kappa is this constant depending on q. So mt is likely to be the smallest integer greater than some function of t. And big M of t also has this property. It's likely to be the smallest integer above this function of t. So on the face of it, this might seem quite surprising. We have this random system involving lots of different fragments of mass that behave independently. When t gets large, we have tons of different fragments. Yet the size of the smallest and largest fragment in the system appears to be behaving deterministically. It turns out that there's the kind of right way to think about this process is not with the t variable as time, but with the n variable describing the type of the fragment as time. I'll show you what I mean by this. So before doing this, here's a kind of depiction of what's going on in our stochastic process. The largest fragments have size roughly 2 to the minus, or the largest fragments at a large time t have size 2 to the minus little m of t. And the smallest fragments have size 2 to the minus big M of t. And up to a very rough order, the size bias fragment, or the typical piece of mass, has size 2 to the minus kappa log t. So that kind of describes the evolution of our cloud of branching Markov chains as time passes. Now, as I mentioned, there's actually a far better way of thinking about this process that makes the concentration of these random variables, little m and big M of t, or the kind of deterministic behavior they have, far less surprising. And we can think of this fragmentation process as a branching random walk. What we do is, on the line n equals 0 here, we just drop 1 point, and this point corresponds to the depth time of the first fragment. Then on the line n equals 1, we draw 2 points corresponding to the depth times of the two fragments of size 1/2. And more generally, on level n, we draw 2 to the n points corresponding to the 2 to the n different times at which a fragment of size 2 to the minus n broke. Now, thinking about the process this way, the points on each line behave like a branch and random walk, where if I'm on generation n, then my position is my parent's position plus q to the minus n times the standard exponential. Because if my parent had size 2 to the minus n minus 1 and died, my lifetime was an exponential of rate q to the n. So my position is my parent's position plus q to the n, q to the minus n times the standard exponential. So you'll see that as n increases, this sort of bunch of points is sort of curving this way to the right. It's kind of curving away from the vertical axis exponentially in n. And there's a better way of thinking about this process by kind of normalizing for this curving or this exponential growth of n. So here we've got two pictures. On the left we have our branch and random walk. This is the way of thinking about the fragmentation process, where on level n we've plotted the 2 to the n depth times of fragments of size 2 to the minus n. On the right, we've normalized all of these depth times by q to the n. So this process on the right, where we've recentered the 2 to the n depth times by q to the n, is a kind of discounted branch and random walk. And this random walk is governed by the behavior that my own position is a fraction q of my parent's position plus my own standard exponential random variable. So if q is equal to 1/2, I only remember 1/2 of my parent's position, and my own position is 1/2 of my parent's position plus a standard exponential. Now, it turns out that this normalization means that in the blue picture on the right, the typical position of sort of most of the particles at level n have order 1. In fact, we can be more specific. A uniformly chosen particle on level n of the blue picture is distributed according to this random variable, kn, where kn is a geometric sum of exponential random variables, but with geometrically decreasing weights. Now, it turns out that in this definition of kn, you can actually set n equal to infinity, and you still get a sensible, positive random variable with finite expectation that's almost surely finite. So when n gets very large, roughly speaking, the typical position of a particle in the blue picture on level n is distributed according to k infinity. And actually, we can say something stronger than this. You'll note that in the blue picture, the position of a particle on level n is a standard exponential plus q times their parent position. That means that they only depend by a proportion q on their parent position. And by extension, they only depend by a proportion q squared on their grandparent's position and q cubed on their great-grandparent's position. So this process on the right is very forgetful about its ancestry. And this means that for most of the particles in the blue picture on a high level n, they behave more or less independently. So let's just recap on what I just said. In this blue picture, which is obtained by recording whose nth level is obtained by recording the 2 to the n depth times of fragments of size 2 to the minus n and multiplying those by q to the n. In this blue picture, the particles on level n behave more or less like 2 to the n independent copies of this random variable k infinity. And using this idea, it's possible to now tackle questions involving the smallest and largest fragment. So this random variable k infinity, it can actually be described explicitly. There's a formula for the distribution function of a sum of exponential random variables with different weights. This formula is in Feller's famous book on probability. And when you let your weights be equal to, or you let your rates be equal to q to the n, or sorry, q to the minus n, then it turns out that you get this formula for the distribution function of this strange random variable k infinity. If you stare at this formula, it's clearly quite complicated, but when s equals 0, it's not clear that when s equals 0, this formula on the right-hand side should be equal to 1, because it's the probability that a positive random variable is positive. It's not immediately clear from the formula that this is actually the case, but it turns out that the fact that this formula is equal to 1 when s is equal to 0 is a consequence of certain identities in algebraic combinatorics. And this is why we use the letter q, because these quantities of phi j of q are usually written using this parameter q in the algebraic combinatorics literature. By the way, I've tried to look, but it's one of those things that's a bit difficult to Google. Does anyone? I'd love to know if anyone's encountered a sort of random variable like this before. Yeah, I'll speak to you afterwards then. Yeah, I'd love to hear more about it. Yeah, so yeah, we have this strange random variable. And in short, we want to understand if we have a large number of independent copies of this random variable k infinity, what do the smallest and largest copy look like? So we're now equipped to give the full story of the largest fragment at time t. So in order to describe the largest fragment at time t, so 2 to the minus little m of t, by changing our perspective, we can instead ask a related question: when did the last ever fragment of size 2 to the minus n die? And that kind of change of perspective gives us a question that's far easier to answer. So the last time a fragment of 2 to the minus n died is roughly q to the minus n, undoing the normalization, times the maximum of 2 to the n copies of this random variable k infinity that has this complicated distribution function here. Now, in order to describe the maximum of a lot of copies of a random variable, all we need to do is understand the upper tails of that random variable. So when you set s equal to infinity, or when you set s very large in that formula above, it turns out that this quantity on the right-hand side just concentrates on its leading term when j equals 0. So actually, this random variable has quite nice exponential tails. And there's a well-established literature for describing the maximum of a bunch of random variables with exponential tails. So since this random variable has exponential tails, it turns out that the maximum of 2 to the n copies of this random variable behaves linearly in n. It actually behaves like gamma n plus an error term. Gamma here is log 2. And this error term, gn, actually converges to a random variable as n tends to infinity. In fact, we can even be more specific about this process. So we're actually able to describe not just the last ever time that a fragment of size 2 to the minus n existed in the process, but also the second last time or the third last time. So I'll show you what I mean by this. So if you take the points of the generation n discounted process and subtract gamma n, and don't worry, I'll draw a picture for this in a moment, then the resulting point process converges to a Poisson process with this density. And this means that actually the distribution of the last ever time at which a fragment of size 2 to the minus n existed converges once properly rescaled. And finally, when you look at the processes at level n and level n plus 1, when n is large, they behave more or less independently. So this means the last ever time a fragment of 2 to the minus n existed is completely independent of the last ever time at which a fragment of 2 to the minus n plus 1 existed. And there's a lot to take in here, but perhaps it's best shown with a picture. So on the left here, we have our fragmentation process. And on level n of this picture on the left, we have 2 to the n different points that describe the 2 to the n different times at which a fragment of size 2 to the minus n died. Sorry, it's a really long sentence. And then on the right, we have the process on the left, but with level n multiplied by q to the n. The result on the previous slide says that if we zoom in, the result on the previous slide says that the rightmost edge of this blue cloud increases linearly in n, roughly like gamma n. And moreover, when you zoom in on a patch of this blue cloud, and look at the sort of particles that are occurring, you'll see that they're forming a sort of point process, and the density of this point process is e to the minus s times a constant. So as you travel left, particles are getting exponentially more common. So when you undo the normalization we just had, this means that the sort of rightmost point of this red cloud at level n occurs roughly at gamma n times q to the minus n. So this result we had just there explains the concentration of mt. Remember, 2 to the minus little n of t is the size of the largest fragment at time t. And if we take a time t, just the usual time, say t equals 1 billion, then it's quite likely that this time t that we just chose occurs between 2 points of the form gamma n q to the minus n and gamma n plus 1 q to the minus n plus 1. So if I have my time t here, and I look up to see what the size of the smallest fragment is, it turns out that there are actually tons of fragments of size 2 to the minus n plus 1, and no fragments of size 2 to the minus n. Because we know that the last ever fragment of size 2 to the minus n plus 1 died after t, and the last ever fragment of size 2 to the minus n certainly died before t. So this explains why little n of t is so concentrated. Now I just want to touch briefly on a qualitative aspect of these largest fragments. When you have this random variable k infinity, it's a geometric sum of exponential random variables. And you can ask yourself the question, given that k infinity is very large, how did it happen? I.e., what can we expect from the constituent exponential random variables, wi? It turns out that when this random variable k infinity is very large, the way in which it is large is that w0 did all of the heavy lifting. So w0 is term of the largest weight, q to the 0, or 1. It turns out that w0 was just really large, and the other guys were all fairly typical. This means that when you relate this observation to our fragmentation process, this means that when you look at the last ever fragment to have size 2 to the minus n, it turns out that the reason this fragment had size 2, was the last ever fragment have size 2 to the minus n, is not because this fragment was born particularly late, it's just because it had a really long lifetime. Well, actually, when we study the smallest fragments, we'll see something very different, actually very different behavior emerging. So we now discuss the smallest fragments. So again, we have this random variable k infinity, and again we have our heuristic. That the time that the first ever fragment of size 2 to the minus n broke is given roughly by a decimal. We're using the fact that if we want to describe what the smallest fragment at time t looks like, we can kind of flip our perspective and instead tackle the question, who is the first ever fragment of size 2 to the minus n to break? But now we have this heuristic, the first ever fragment of size 2 to the minus n to break is roughly q to the minus n times the minimum of 2 to the n random variables k infinity. Now, rather than the upper tails, we need to understand the lower tails. So we need to understand the probability that this random variable k infinity is extremely small. Now, if I have n independent exponentials, and I have a bunch of positive weights, a1 up to an, then when you think about it, the probability that this weighted sum of exponentials is smaller than s, this probability is at most s to the n. If you think about it as s tends to 0, or it's a kind of polynomial of the order s to the n. Now, if I have a bunch of positive reals with a finite sum, I can define a nice random variable, this infinite sum aiwi, where wi are standard exponentials. Of course, the expectation of this sum is finite, so the sum is certainly finite. The expectation of this sum is just equal to the sum of the AIs. But now, If I consider the probability that this infinite sum of exponentials is less than s, and I consider these asymptotics as s tends to 0, then since this sum is bigger than its first n terms, it has to be the case that this quantity goes to 0 faster than any power of s. So it means if you look at the asymptotics of this quantity here as s tends to 0, it certainly have to be smaller than s to the 100 or s to the million. And when you think about it, you start to try and think of functions that go to 0 as s goes to 0 faster than any power of s. You might think of things like e to the minus 1 over s. That's an example of a function that goes to 0 faster than any power of s. So we know that, coming back to our specific sum, where the weights ai are powers of q, we know that this quantity, given by the probability that k infinity is very small, is smaller than s, it has to be some sort of quantity that goes to 0 faster than any power of s. And we'll see actually that the way in which it does this is it looks like e to the minus log 1 over s squared. So we have this result. If you define this bizarre function, where it roughly looks like kappa, it roughly looks like a constant times log 1 over s, plus a bunch of other terms, then it turns out that up to some constant order, e to the minus f cubed of e to the minus this bizarre function captures how fast this probability goes to 0 as s goes to 0. So this function here characterizes the lower tails of our random variable k infinity. And we can use the formula on the previous slide involving this really complicated function. We can use this to deduce that the smallest of a large number, 2 to the n copies of this random variable k infinity, has roughly this order, square root n minus a log term. So again, coming back to our picture, on the left we have our branching random walk, where on level n we have the 2 to the n times at which a fragment of size 2 to the minus n broke. And on the right we have those times multiplied by q to the n. And this time, rather than the right-hand side of this picture, we're trying to look at the left-hand side. And we find that this left-hand side at level n is roughly the exponential of minus wn. And in particular, that means that the first ever fragment of size 2 to the minus n to break broke at a time roughly q to the minus n times the exponential of minus wn. While in the largest fragments case we have a description of the point process describing exactly the largest and second largest and third largest fragment of size 2 to the minus n to break. We had a description of the point process describing the last, second last, and third last fragment of size 2 to the minus n to break. We don't have a rich description of the first ever ones to break. We don't know exactly what this picture looks like on this left-hand side. But anyway, we do know, roughly speaking, that the first ever fragment of size 2 to the minus n to died at this time here. Q to the minus n times e to the minus w. Again, we have a similar story where if you pick a large time t, this large time t is likely to sit between two of these points. And when you go up, what you'll find is that there's some n for which there are likely tons of fragments of size 2 to the n plus 1, but no fragments, 2 to the minus n plus 1, but no fragments of size 2 to the minus n plus 2. And this explains the concentration of this index big O of t, describing the size of the smallest fragment at time t. Now, perhaps interestingly, the behavior in which the smallest fragments emerge is kind of qualitatively different to the behavior that leads to the largest fragments emerging. When you look at the last ever fragments to have a certain size, it turns out that, as I mentioned before, these fragments had fairly typical parents. If I was the last ever fragment to have size 2 to the minus n, it's quite likely that my parent of size 2 to the minus n minus 1 was just a regular fragment. Just a typical person fragment. Whereas with the smallest fragments, the story is very different. If I'm the last If I'm the first ever fragment of size 2 to the minus n to die, it turns out that I came from a recent lineage of very small fragments. My parent was likely one of the smallest fragments of their generation, and their parent was probably one of the smallest fragments of their generation. So now just a summary of what we've seen. So we studied the fragmentation process where a fragment of size 2 to the minus n has an exponential lifetime of rate q to the n before breaking into 2 equally sized pieces. After scaling by q to the n, we found that the 2 to the n different times at which a fragment of size 2 to the minus n breaks are approximately distributed according to 2 to the n copies of a certain random variable, k infinity, where k infinity is this strange random variable which is an infinite geometric sum of standard exponentials. The upper tails of this random variable k infinity are nice. They just behave like exponentially. And that means you can just get quite a rich description of the maximum of 2 to the n copies of this random variable k infinity. In fact, you can describe the maximum in terms of a Poisson process centered around a certain point. The lower tails of this random variable k infinity are very complicated to describe as s goes down to 0. But you can sort of, up to constant order, get some description of these lower tails. And that means that you can describe to a reasonable degree of accuracy what the smallest of 2 to the n copies of this random variable k infinity look like. These descriptions of the maximum of 2 to the n copies and the minimum of 2 to the n copies of k infinity lead to very sharp descriptions of little m and big M of t, which are the stochastic processes governing the size of the smallest and largest fragment in our fragmentation process. And that concludes the talk. Thank you for listening.
Thank you so much for the lovely talk, Samuel. Are there any questions?
Maybe I can comment. If I'm not mistaken, behind this random variable, actually is exponential functional.
Sorry?
I think behind k infinity is actually exponential functional for a big process, with a special case when you have counting pose on pose, but not with mass 1, but with momentum, let's say 1 over q.
Oh, really? So have you seen something like this before?
Yes, and there is some literature which probably gives you the large asymptotic, so there is some link, let's say.
I'd love to see it.
Yes, I can point you to some, but I think it is behind.
Oh, yeah, I'd love to see it.
Thanks for excellent talk.
Yeah. Thank you, man.
Yes?
So maybe just starting at the beginning of the talk, but my question was, so when I imagine a stonemason making on stone, and maybe the stone falls into 2 pieces, but then there's still a small piece falling also into dust, which cannot be used. So this would correspond to losing mass in every step. Is it still does it still fall under fragmentation, and then depending maybe on the amount of dust, is it seen in this model as a drift?
Yeah, so it's a good question. Yeah, and we're currently looking at it also with the team of 5 authors I gave at the start, and also Sandra Blau. We're looking at the case of general fragmentation processes, where you don't split into. I lied, it's not actually 2 equally sized pieces, but it can be k equally sized pieces for any integer k. You get a very similar story to what I described today. But we're now studying more general fragmentation mechanisms, where you do get very small pieces emerging immediately. But we still anticipate somewhat similar behavior with the largest fragment. And actually, the results can kind of continue to hold even when mass isn't conserved. So you have some sort of mechanism where a fragment of mass 1 could break, quote unquote, into a fragment of mass 0.6 and one of 0.5. So it doesn't necessarily need to add up to 1, but there just needs to be some sort of control for the way mass behaves. I'm not sure if that exactly answers.
Yeah, so what I'm thinking of is maybe the mass which falls into dust is dependent on the size of the hammer somehow.
Yeah.
So this would also change behavior, because then at some point maybe it's the whole process stops at some point, because you cannot split anymore. You cannot lose dust somehow.
I think what you said at the start is you can consider non-conservative fragmentations where the mass adds up to less than 1. and the average amount of mass decays exponentially. And I think you said it, that it probably just adds something like a drift to the size of the largest discrete fragment. But yeah, it's a big thing. Thank you.
So could you go back to your main theorem?
Yeah. This one?
Yeah. So I was wondering at this point whether exactly at the place where t where this expression becomes an integer, should you see the gumball somehow?
Yeah, it's a very good question. So this is actually an abbreviated version of the main result, where this result is only kind of true when neither of these quantities are too close to being integers. And the way we actually phrase the result is when this quantity is very close to being an integer, there's actually a small window of time in which exactly little m can be two different integers and big M can be two different integers. And yeah, and as you might expect, it's possible to describe that window.
In my opinion, you can correct me if I'm wrong, for any fixed m, this distribution is hypoexponential. Have you tried to use the cumulative distribution function of hypoexponential distribution? You can take power n and you will obtain, at least from mathematical point of view, some new result, in my opinion.
Agree.
There is a hypoexponential distribution, and in my opinion, this is a particular case of hypoexponential distribution when the parameters are of for 2 to the power minus n or something like that.
Right.
2 to the power I, yes. And you can take the formula for the cumulative distribution function of the hypoexponential distribution to make limit. And this should be this cumulative distribution function of k infinity. And when you take this distribution to the power m to the power n, this should be maximum. The cumulative distribution function of the maximum. And maybe this is a different way to prove your results.
Right, yeah. So are you saying there's some sort of literature on these sums of exponential hypoexponential?
This is hypoexponential distribution, sum of exponentials with different parameters.
Okay. But yeah, that's very interesting. Perhaps I could ask you more about it afterwards. Yeah. Thank you.
So some other questions, remarks? Yes?
Just a comment. Branching processes with energy introduced by Peter May are an example of fragmentation also, where energy of the particle is divided between two the particles and so on. But in branching process, I'm interested in another thing, of course. And the more complicated example is so-called pulse-labeling of the cells, where the label of the cells is divided between two delta cells, but it's more complicated because when the cell died, label disappeared, and so on. Right. But this is an example of fragmentation, but from branching point of view, another problems are interesting.
Right, so this process has been studied from a slightly different point of view.
Yeah.
Thank you.
Also, other questions? If not, let's thank our speaker again. So we will continue at 3 p.m.
Sorry, I just want
This is Krzysztof about this these functions. The densities of these functions. Exponentials with different.
Oh, really? Sorry, can I take a look? What your frequencies?
These appear as statistical games, I suppose, moving that weird functions. And they have been started in the 60s.
Really?
Some asymptotic results for pair densities.
Right.
So possibly find statement of theory somewhat literature, but they're not claiming that you can't read.
Right.
Anyway, this is really nasty class of functions, but they have a nice amount of purpose in some sense. That might be just a useful reference. I'm not claiming that that's just your comment about the explanation. You did help with the theory that I found on your co-author. Yeah, exactly. So that's just about the distribution of the individual variable. And then moving forward, if you have independence finally, then it's probably pretty easy, but then you don't really get a grasp of how independent they really are. It sounds like a challenging thing.
Yeah.
But it's really available. Sorry? It's already available.
Yeah.
It's pretty exciting.
Oh, thank you. Thanks.
Yeah, if that's useful.
Yeah. I'll check it out. Thank you.
I have a job in Bristol, but I don't go there. My job requires me to keep going to the distance part, so I have to go to meetings and that, but actually most of the time. In fact, my job in Bristol ends at the end of August, so I think it's well, I have an office in there, but I don't go there very often. I don't know, this is there. Or travel, it's I'm not there every day. The interesting thing about COVID is how quickly you forget. That's something to reverse to. I remember is an injury. As soon as I run in Bulgaria, I started asking, what's the new story? It's not obvious that so they use English Russian. I know this is that would be that's also a problem.
Okay, it's perhaps time to resume this afternoon session. So right now we have the pleasure to listen to Martin Liss from the Technical University of Vienna on the topic of a duality between height functions and continuous spin models. Martin, the floor is yours.
Thank you, Ivan. Thank you very much for the invitation to this very nice meeting. This very beautiful city. It's the first time for me to be in Bulgaria. So I would like to say something about my recent work with my PhD student, Diederik van Engelenburg, who is at the University of Vienna. And the program for the talk is the following. I will first tell you about something very classical in physics, which is the Berezinski-Kosterlitz-Towers phase transition and continuous spin models on two-dimensional graphs. I will tell you about the heuristic and a comparison with the Ising model, and I will state some results. And then to go maybe to the proof part, which is point 4, I will have to go back, take a step back and tell you about this general framework that exists in statistical mechanics, which is called abelian duality between different models of statistical mechanics. So when I'm done with that, I will tell you about the different phase transition, which is a phase transition in a model which is dual to a continuous spin model, which is a model of height functions. And then, time permitting, I will tell you about a new short proof of the fact that this localization, delocalization phase transition in height functions implies the BKT transition in continuous spin systems. And yesterday I realized that I'm one of the few people who will not actually have a stochastic process in my talk, so sorry for that. Everything will be quite static, except that maybe I will show you a simulation of the model interest. So for comparison, these are pictures of the easing model on the square lattice. So the easing model is a very classical model of statistical mechanics. So you put on each vertex of a big piece of the square lattice a spin, which in the easing model is just plus or minus 1 value. And then you sample a configuration of such spins from a distribution which is biased from the uniform distribution by this exponential factor, so this Gibbs-Boltzmann factor, where you have a parameter 1 over the temperature, so the temperature is the parameter of the model, and then there is the energy of the spin configuration. So what you do is for each edge of the square lattice, for each bond, you look at the two neighboring spins, sigma u and sigma v, or sorry, here sigma u, sigma v prime, and this should be a v. You take the product of these two spins, and you add this up. So you see that this probability measure favors configurations where two neighboring spins have the same sign. Then the product is just plus 1. So it's very classical now that if you look at the big picture, so a big graph or even an infinite graph, there's 3 different phases in the model that you can basically see with your own eyes. So you can see sort of in a geometric picture when you sample the model that there is a phase, the high temperature phase, for example, which is usually the easiest to study, where the configuration looks very random. It looks like a TV screen. So here, say, the blue spins, or the blue pixels are minus 1 spins. On the other hand, there is a low temperature phase. At some low temp, for temperatures lower than some critical point, your configuration basically looks like only the spins that you put on the boundary. So here I put just white or plus 1 spins on the boundary, and if the temperature is low enough, basically the system tends to be all white, as you can see. And there is a critical point where things are different, and it's a completely different story that I will not go into. So this is one sort of pictorial geometric point of view. You can basically see the 3 different phases, but you can also distinguish between some observables of the model. So I will be interested mostly in these 2 phases, the non-critical phases. So for the easing model, if you look at the high temperature phase, the expectation of the spin inside a big box or inside an infinite lattice, it will be 0 if the temperature is large enough, even though you put some plus 1 boundary conditions which favor the spin in the middle of the box to be actually plus 1. If you look at the 2-point function, so the expected value of the product of the spins, and you take these 2 spins or the 2 points far away, then in this phase there will be exponential decay of this 2-point function. And there is a different behavior, completely different behavior in the low temperature phase. We say it's an ordered phase, which means that the spin in the middle of the box actually remembers the boundary conditions. So the expected value will be positive, even after you took this infinite volume limit, say. And for the 2-point function, it will also stay uniformly positive, so it will not even go to 0. So this is very classical, and this model is actually special. You can compute all these constants explicitly that I wrote here, but I will not go into that. So that's a very simple, yes, sorry.
The question, maybe it's confusing. In your first formula, is mu the same on the left and right hand side, or mu on the left is meant to be density?
I'm not sure. Sorry, this is the...
It's just a measure.
Mu is a measure. So I will call my measures mu, sorry. It will not be p, it will be nu and mu for my method. So you can ask a similar question for a model which is slightly more complicated, where you put the spins to be not plus minus 1, or but you want them to live on a circle. So you can think of having an angle between minus pi and pi, and now you bias sort of the uniform independent law on such spins by a similar Gibbs-Boltzmann factor, but now you compute the energy slightly differently because it's a different space. So you look at each edge, and for each edge you look at the cosine of the difference of the angles. So this function is the largest when these 2 angles at an edge they agree. Okay? So you favor configurations where angles are close to each other for neighboring spins, and the amount of price that you pay for having different spins is modeled by the temperature parameter again. So here you can see, okay, also 3 different temperatures from high to low, and you can start to wonder what is the behavior in this model. Okay, so here it's clearly disordered, and on the right, when you decrease the temperature, it seems like all these spins actually try to point in the same direction, so the cosine should be almost 1. And so things of this type may be the 2-point function. This is a measure, say, in the infinite volume limit. I will not go into the details how you do it, but you can take limits, and if you impose +1 boundary condition, so +1 you think of the spin pointing to the right as on a unit circle, then you can ask a question: what is the behavior of these observables? Okay, here is a more colorful picture. Here again, it's like for easing, very disordered, but you see that if you decrease the temperature, okay, so here it was 7 by 7, and here it's 1000 by 1000, and the colors, they denote the angle. So there is a rainbow of colors around, on a circle that you can draw. And you see that even though the temperature is very small, and in this picture here, it seems like they all want to point in the same direction. Here, there is big patches where they want to point in the same direction, but you actually see that all colors exist in the picture. So there is no preferred color. So the system doesn't choose a color. It chooses a color locally, but not globally. So
for this picture on the right, what's the boundary condition? Sorry.
So this is, I think this is free. Anyway, for the model, for this model, the boundary conditions in the end they don't matter because of this theorem, which tells you that in this model, actually, you don't see the ordered phase. For the easy model, the existence of the ordered phase follows from the fact that if you look at the model, you can fully describe it by these closed circuits which separate pluses from minuses. And you see that if the temperature is very low, the existence of a circuit is very costly in terms of energy. So you can make like a combinatorial argument, which is called the Pios argument, which is a very important argument. You can make an argument to show that this phase actually exists at low temperature. So this is no longer the case in this model because, well, first of all, you don't see the contours clearly, and second of all, the spins can change sort of continuously. So there is no fixed price that you have to pay and that you can make very high. And actually, you can make a computation, you can actually prove that you see here is a configuration where everything points to the right, but in the middle you're pointing to the left. And you change very slowly to that pointing to the left in the middle. And you can compute the energy of this configuration and show that the cost of it in the infinite volume limit is actually 0. So you will see these things happen basically everywhere. So you have spins pointing in all directions always. And this is a famous theorem of Mermin and Wagner. And it's a very short theorem. You can find it in the book on statistical mechanics by Velenik and Philippe, for example. So in this model, there is no phase transition in the sense of easing in 2 dimensions. And this is not true in dimension 3 already, it's also proved mathematically. So this is something very 2-dimensional. And if you want to talk about the 2-point function rather than the 1-point function, that is also was proved quite a while ago, that the 2-point function always decays at least as a power law of the distance at any temperature. And as I said, the sort of high temperature regime is always easier to study in statistical mechanics. So in particular, exponential decay for the 2-point function at high t is always very easy to establish. So having this picture in mind, you can ask the question, is there any other phase transition in the model of any other type than the easing phase transition? Or is it the case that the 2-point function, for example, decays exponentially fast at all temperatures? And this was unclear still in the 70s in the physics literature. People, the computers were not so good, so people couldn't really sample these things very well. But there was 3 people, okay, 2 separate groups, Berezinski separately and Kosterlitz-Taules separately, who proposed a heuristic, or in physics maybe it's a proof, that actually there is a phase transition in this model. And they said, okay, let's look at this geometric picture, like in the easy model, but here we should look at something else. We should look at these points where you have a full rainbow around a single point. Which means that it's a point in your, say, model where you actually make a full turn around some microscopic region. And they call these vortices and anti-vortices, so you either turn clockwise or counterclockwise. So so here it's maybe more visible. You have these points, these sort of squares in the lattice where your arrows actually make a full turn if you go around this microscopic phase. And these are, they call them topological excitations of the system. And hence the name topological phase transition also that is used for this phase transition. So they argued that, and they argued the following. They did a computation, which I actually don't know myself, but I know the big picture. They said that you can describe the system as a collection of, random collection of points. Some of them are vortices, some of them are anti-vortices, and they interact through a potential, which is logarithmic in the distance. Okay, you can try to compute that. And then they said, okay, because the potential is logarithmic, you can actually see that, okay, at very high temperature, you will have very many vortices and anti-vortices. The arrows point everywhere, anywhere. It's very disordered. So they call this phase the plasma. But they said that if you start decreasing the temperature, there should be a point where the energy wins over entropy, and you should see configurations where these vortices and anti-vortices, they're meeting pairs, because that's where the energy is the lowest. So they want to be close to each other. So these vortices and anti-vortices, they want to be close to each other energetically. And then you should see a picture like that. So that was as far as I know, their argument. And 2 of them got the Nobel Prize in Physics in 2016. And Berezinski died in the 80s, quite young. Okay, so that's one heuristic, but I will have another heuristic which I understand better. But it's also quite bad if you want to make it rigorous. So another heuristic is the following. You can sort of pretend that your spins are not on a circle but on the real line. Okay, just do that. And then you can say that at low temperatures, cosine, first of all, the angles should be close to each other from neighboring sides. So the cosine of theta, it should be a cosine of something small, which is like 1 minus 1/2 square of theta. So you do these 2 operations, which are not justified at all. And then you see that your model, your theta field, is actually what's called a discrete Gaussian free field. So it becomes a Gaussian model because of the square potential. And you can actually analyze it completely. It's one of the most studied random fields. I will talk about it later also. So if you do that, you can see that, if you want to look at the cosine of the difference of the angle, you can actually write it as the expected value of e to the I theta 0 minus theta v. You can do it because the system is symmetric, so it doesn't matter if you add the complex conjugate or not. And this is just the characteristic function of a Gaussian random variable then. So you just need to know its covariance function. So this is just the characteristic function, so it's minus 1 e to the minus 1/2 the covariance. And the covariance for the discrete GFF is just the green function of random walk. So it's the simplest probabilistic object you can hope for. So in 2 dimensions, this green function has a logarithmic behavior. So by this computation, it's just e to the power some constant times logarithm. So this heuristic tells you that at low temperature, the 2-point function should be actually a power law decay, not exponential. So what's missing until now to establish that is a lower bound at low temperatures. So we have an upper bound by this paper of McBride and Spencer, and the lower bound is still missing. Okay, and maybe I show you a simulation as promised. Okay, so here, what did I do? Okay, let's try to increase the temperature. So this is a very disordered place. I think this is some blubber dynamics. And if I go to sort of, okay, slightly smaller temperature, the clusters of colors get bigger and bigger. And if I really put it very small, you see this picture which will change very slowly, but by the absence of symmetry breaking or this easy phase transition, you actually see all colors in the configuration. So this is heuristic, and there is actually a theorem from the 80s, which is a famous paper of Froelich and Spencer, who established this behavior. So they proved that indeed at low temperatures the two-point function doesn't decay exponentially. So there is a phase transition in the end. And what's interesting is that this paper, okay, maybe is inspired by the first heuristic, but the proof really doesn't follow the computation of the physicist. The proof uses the duality from the title, and first establishing a phase transition in a completely different model. So this paper also is famous for being quite difficult to understand. So it's very technical. It uses some multi-scale analysis, and it's really hard to read. So what happened 2 years ago is that we, together with Diderik, and also independently there was another set of authors who gave a new proof of this fact, which we call elementary in the title of that paper, which today I still think is a good description. So we give a simpler proof of that fact, following the same sort of philosophy as Froelich and Spencer. So first using a different phase transition in a different model, and then using duality, trying to translate that into this BKT phase transition. So the other thing was Eisenman, Harald, Pellet, and Shapiro. Yeah, so these two papers appeared on the archive on the same day, not 2 years ago. Not even 2 years ago. And there is a new paper by myself and Diderik from 2 weeks ago, where we give an even simpler proof of that fact. And I think we'll stop here, so there will be no third paper. And the idea of this talk is to try to give you some flavor of the proof. Okay, but for this, so for this I need to take a step back and do introduce some general theory, which I think is it's a good idea to talk about it in generality. Sometimes it's nice to have a general statements, and then we can see somehow similarities between different models. So I decided to state it in full generality that I know, and not only in the generality that we use in the paper. So it's something very classical, but also I think very beautiful in two-dimensional statistical mechanics. So the setup is the following. You start with a graph which is planar, so drawn on a plane, and you can just think of a piece of the square lattice as before. And then you have a group. So the group for the easy model was just Z2, and the group for this XY model is just a circle group with multiplication. So I say here locally compact, but I don't really care much about that. It's just a abelian group. And for the examples, I will talk about the real numbers, the integers mod Q, so a finite cyclic group, and the application will be a duality between the integers and the circle, which is known as a Fourier series duality also in just analysis. And then I have a potential which defines my statistical mechanics model, which is a function from the group to the real numbers, which is symmetric, and I will use the abelian notation the additive. I will use the additive notation for abelian groups. So I will write the minus G for the inverse element. And you can think of this potential as being the smallest on the identity element of the group. So it doesn't want, so it will be applied to the product of an element at the vertex and an inverse element at the vertex nearby. So it wants these two elements to be the same element of the group. So it wants to assign the smallest energy to that configuration, so it will have the smallest value on the identity element. And then I just define the statistical mechanics model in a similar way as before. So I have a measure, nu, which is a biased version of independent spins on every vertex. So I first put independent spins on every vertex, where the distribution is sort of uniform on the group. So it's according to the Haar measure. The Haar measure may be not the finite measure if the group is not compact, but okay, you can think of it as just a uniform measure. And then you bias it by the same sort of formula. So you have an energy of a configuration, which is just sum of the potentials of the differences or the gradients or G times G inverse for every edge of your graph. So that's the most general definition in this sort of framework. You can think of it as a gradient model because it really looks at the gradient of the system on every edge. And then there is a temperature parameter as before. So the main question, anyway, in statistical mechanics is what are the large-scale properties of such measures? In particular, is there a phase transition? Is there a drastic change if you change this parameter t? Okay, so the examples are, for example, the Ising model, as I said before. With this potential, there is a classical Potts model, which is, say, the group of Q roots of unity with a very simple potential, which is just the Kronecker or minus the Kronecker delta of the identity element. In this model, you only pay a price where two neighboring spins are different, and that's the only thing that you care about. So these are finite groups. There is the Gaussian free field that I mentioned, which is a very important model, and it will appear later on as well. So here the group is just the real numbers, and the potential is quadratic. So that's why you get the Gaussian field. But it also fits this abelian spin model picture. So these are models that are in the background, which have the same property, but the main object of interest are the groups, which is the circle or the angle, and the XY spin model. So as I said before, so this is the same potential as before, but written slightly in a different way. You can think of a spin either as an angle or a complex number of length 1. So either theta or sigma. And here V is just the same potential as in the second slide. So far, this is the continuous spin model. And what is a height function? So that's also from the title of the talk. A height function is a sort of spin model whose values are integers. So it's a model on a graph where each vertex gets an integer value, and there is a probability measure which somehow penalizes different values of this spin to be far away from each other. And for example, you can take the same potential function, which is just the square, but restrict your attention to the group of the integers. And this is called the integer value GFF. So it's not a Gaussian model, but the name comes from the similarity with the Gaussian model. So in the future, in this talk, there will be a relation between these two models. That's why I highlighted them. Okay, so to state the duality, you need to know what a dual group is. It's called a Pontryagin dual group. So every such abelian group has a dual group, which is the group of group homomorphisms to the complex circle. Elements of this group are sort of called characters. So every such abelian group gets a dual group G bar, which are all the homomorphisms to the circle. And then you can convince yourself that, for example, the dual of ZQ is ZQ, with these exact characters, as I wrote here. Or the dual of the real line is the real line with characters of this type. And so this is these cases are called self-dual for that reason. And so the interest of this talk is in the non-subdual example, which maps the integers. So the dual of the integers happens to be the complex circle actually. So how do you actually produce a homomorphism from the integers to the circle? Is you actually fix a number on the circle and you start raising it to the power of that integer. These are the only homomorphisms from Z to S. And that's why the dual of Z is S. And vice versa is the same thing. So if you want to look at the dual of S, what you do is you fix an integer, and the only way you can do a homomorphism from S to itself is just to raise the numbers to some fixed power. So this is the duality in this case. So sorry for being slightly abstract here. So that's the Pontiac part of the name, and there's a Fourier part of the name which comes from the Fourier transform. So once you have such a such duality, you can look at the Fourier transform, which maps every integrable function on your group to a function on the dual group, and you do it in your in the classical way. So chi is a character, so it's an element of the dual group. So what you do is you integrate your function over your original group against the Haar measure, but you multiply it by a character, say, okay, a complex conjugate. And if you look at, say, this case, which is the real line, and also this case, which is the circle of periodic functions, then you really recognize just the Fourier transform. Okay, so this is sort of the abstract framework. And I will say that the function is positive definite if its Fourier transform is non-negative or positive, say. Because for the duality, I would like to have something which is dual to something positive, because it will give me a probability measure. Okay, so coming to the duality itself. So if you start with a potential such that this function, this Gibbs factor, is positive definite, it means it has a positive Fourier transform, then you can write this Fourier transform as e to the minus u. Just take a logarithm of it and then minus that, and you define u as a function of the dual group. So basically you can define a potential function of the dual group. And you can study the same type of model with values in the dual group. But to do it, you actually have to look at the dual graph as well. So if you start with your, say, square lattice, G, then your dual graph is the graph where the vertices are the faces of your original graph. Maybe I have a picture here. Yes, so if the black thing is your original graph, then the dual is also a square lattice in this case, where for every face you have a vertex and there is an edge. There's always an edge which crosses your original edge. So this is called the dual graph. So for this Pontryagin duality, we have lots of duals. We have the group becomes dual and the graph becomes dual. But once you fix that, you have the following identity, which is an identity for expectations of some observables of the models. So on one hand side, you have a measure, which is your original model, on your graph G, with values in your group, also there's too many things, sorry, in your bold G. So these are these random elements. And what you can do on the left-hand side is you can fix some characters, take products of them, and look at expectations of such objects. These are called order observables, or order correlations. And this duality is just, it's a way of translating that to the dual model, so I call this dual model mu. It lives on the G star graph, the dual graph, the red here, and it has the potential u. And there is also a product of things, but it's not the product of something which is called order parameters, but it's called disorder parameters, because here you sort of pretend that what you see here is just the factor that you get from the definition of the model with a plus sign, so it cancels the original one from the definition of the measure, and you replace it with this factor. So basically for these edges where you look at your order correlations, you pretend that in the dual model the gradient is something different than it actually is. It's called disorder operator. It's a twist of your configuration in some sense. On these edges you think that the gradient is actually shifted by this character, because this is the dual group, so a character is actually an element of that, so you can add it to the configuration. I think it's maybe it's not clear, but it's... Okay, so this is the most abstract form of this duality. But for example, what you can do is, if you look at the spin model XY, you may want to look at the correlation of sigma 0 times sigma x bar. Okay? So what you do is you can take these characters on this green line to be equal to the identity character, which doesn't change anything. Because then you will see that, you know, if you go along this line, you have like a telescopic product or sum. So these insertions of G from the middle points will vanish, and you will actually get just sigma 0, sigma x bar. And then you put on the remaining edges of your graph just the trivial character, which maps everything to the number 1. So you can look at this two-point function, the classical two-point function in this very general framework. And what you get on the other side will be a model of height function here, where on each of these edges, which are dual, so cross these green ones, you actually pretend that your gradient is 1 larger. So there will be +1 basically for the gradient. So that's the formula. That's the formula that people used so far in this the proof of the PKT transition. And part of our input here is that you should do the other way around. You should put the height function model on this side and the spin model on the other side, actually. Because you know, if you do duality for Ising pods, everything is self-dual. It doesn't matter which way you put where you put the model, because they are basically the same models on both sides. And here, it's, you know, in the non-self-dual case, you actually have a difference if the order is in the spin model or if it's in the height function model. So this will be one message from today. And the general message of this construction is that, you know, maybe it's easier to analyze one of the sides and then you have information on the other side. So that's a very simple message. This is a very simple idea, but it's very hard to implement in many cases. So here is a list of results, which is quite subjective and personal, where duality was used. So it goes back to 41 for the Ising model. Actually, it's called Kramers-Wagner duality. And it was the first time where, for example, the critical temperature of the Ising model of the square lattice was computed using the duality. Because in this case, the Ising model is self-dual and the graph is self-dual. So you can compute explicitly a temperature where the transformation doesn't change anything in the model. And then you can guess it's actually the critical temperature, and that has been proved. But for example, for the PODS model, the same result is the result from 2010 only. So it sounds like a simple idea, but it's sometimes quite difficult to implement. So these are the self-dual examples, and there are many more, but I didn't have space, obviously. And the conformal invariance result for the Ising model is also part of this story, because what Smirnov proved is that actually these disorder operators are the conformally scaling limit. And for the Ising model, they were introduced by Kadanoff and Cheva. So this all fits into this duality picture. And we want to say something about the non-self-dual case, which is the proof that I mentioned before. Okay, so as I said, for some reason it's easier to talk about the dual model of a continuous spin model, to talk about height functions and prove that there is a phase transition over there, and try to map it back to spins using duality. So I don't know why it's easier, but that's the way it is. Unless there is a new proof. So what is the phase transition for height functions? So you can, for example, think about a height function model on a square, finite piece of the square lattice, where the size of the square goes to infinity, and you put zero boundary conditions. So you have a random integer valued field on your vertices which has zero boundary conditions, and the potential, I mean, it penalizes big differences between neighboring values. So you have a random discrete surface on the big graph set, and you force it to be zero on the boundary. So there should be a phase transition in the following sense. So if your temperature is low, which means you penalize a lot of differences, your surface should tend to be flat. It doesn't want to have gradients which are non-zero, which means that even if you grow this box to infinity, the variance in the middle of the box, it stays finite. We say that the surface is localized. Sorry for not having pictures here. But it's sort of intuitive to expect that if the temperature is high or the potential doesn't penalize a lot, your surface will actually like to fluctuate just entropically. So it will fluctuate to that extent that the variance of the point of the height in the middle actually blows up. So it's the localization, delocalization phase transition. So this is more, maybe it's less subtle than the one for the spin model. And you can actually think of it as also symmetry breaking in some sense, and the symmetry breaking of translations of the integers, even though it's not a compact symmetry, so there's no probability measure which preserves that symmetry, but physicists think of this transition as a symmetry breaking in some sense. So this is a general picture of type 0. The picture of type 1, more difficult, will be to prove that this variance actually diverges logarithmically in n. And this is the quantitative version of delocalization. It's expected to be true in very high generality. And the statement of type 3 is to prove that at large scales, whenever you have a surface or a height function which delocalizes, it should behave as the Gaussian free field. So not only it has logarithmic variance, but the variance at 2 points far away is like a green function. So this is a very general statement proved in few instances only. It's quite a difficult, it's very difficult to prove. It's sort of a version of the invariance theorem of Donsker for two-dimensional height functions. Like in 2 dimensions, you're always delocalized if you look at gradient models. Or sorry, in 1 dimension, you're always delocalized if you look at the gradient models because they are just random walks. And then you always converge to random motion. Here it's like a 2-dimensional version of random walk where the 2 dimensions are the space, not the value. And then you should always converge to the GFF, which is a version of Brownian motion for 2D time in some sense. So it's a very general conjecture proved in many, in few cases, in the strongest form. In the weakest form, it has been proved for different models recently by a few authors. So in recent years there was big progress in that area. An example is a paper of Pete Lammers, which happened half a year before we wrote our proof, and it was the inspiration for our paper. So Pete has a 10-page paper where he proves delocalization transition for many height function models under the assumption that your potential is he calls it excited, meaning that it's a condition which says that you don't pay much for having a change of size 1 between neighboring sites. And it's enough to check it on 2 values of your potential. And he says that if this is actually the case, then your model delocalizes. So this is the harder part of the phase transition, to prove that something delocalizes. So it's a beautiful paper. I recommend, if you like percolation type arguments, this is it's a must to read, I think. There is a weak point of it, is that it only works on trivalent graphs. for example, the hexagonal lattice, so it doesn't work on the square lattice. But I will pretend that it's also for the square lattice. We can handle that case. Okay. So this will be the result that we use. And I actually have time to talk about the proof, which is, I'm surprised. Okay, so I will try to give you the full proof that we have of the fact that if you have a delocalized height function, its dual model, which is a spin model, it cannot have exponential decay of correlations, which is a proof of phase transition, of the BKT phase transition. Okay, so this is the general form of the duality as I wrote before. And if you specify to the case where your group G is actually the circle, so the one that I was mentioning in the picture, so each character is just a natural, or it's just an integer number. So the left-hand side becomes this product, and the right-hand side here is the height function model. So if you look at it, it seems that this is the right thing to use, because on the left-hand side you immediately have the two-point function of the spin model. If you choose this line of these disorders or these chi's. So this is just the two-point function. So you say, okay, this is the two-point function on the right. I have something about the height function. So if I know that it delocalizes, I should try to use it to prove that this quantity here say decays polynomially, not exponentially. But it's actually very difficult, because what you have here is, unlike here, you will have a local observable of the system, a spin here and a spin there. Here you have a complete line of disorders, so it's a macroscopic object in your system. You have a product of a number of guys, and this product, the number of elements in the product diverges. And it's not clear how to analyze it, knowing only that the height function delocalizes. Okay, so our first step is, okay, why don't we do the opposite? Why don't we put the height function model on the left-hand side and the spin model on the right-hand side? So what you get from this is, on the left-hand side is actually just the characteristic function of, I can put any epsilon, so any real numbers actually, it doesn't have to be from minus pi to pi. So this is just a weighted sum of gradients of my height function, and I look at the expectation of I to that power. So it's just the characteristic function of my height field, or the gradient of the heights. So I want to take as an input that the fact that the variance diverges, so I want to have a formula which has variance in it. So how do you get variance from the characteristic function? You just compute its second derivative at 0, and you get variance, okay? And this you cannot do in this formula here, because n is a natural number. You cannot just differentiate in n. So what we do is just differentiate in epsilon. If you do it, so I put a parameter in front of the epsilon, and I call it s, and I take the derivative in s at 0. So I get that the variance of this field, which here is just epsilon inner product, the gradient, so I denote this sum by the inner product, squared. Okay, it's a very simple formula. Involves second and first derivatives of the potential of the spin model. And I call here d theta just the gradient of the angles on edge d. So the first observation that you get is that this is actually smaller than just only this part, because this is evidently non-negative and there is a minus in front of it. So if you assume that this is bounded by a constant, which is the case always, you get that this variance is smaller or equal than the inner product of epsilon with itself. Okay? So now comes a nice property of this formula, is that if you look on the left-hand side here, the only way this quantity depends on epsilon is actually through this quantity. So this requires the knowledge of an adjoint operator in the Hilbert space. So what I do is I start with what I had before. So this is the inner product on the space indexed by edges. and I just move d to the other side and I write d star. Okay? And d star is actually an operator that you can simply write. So d is just a gradient operator, and d star is an operator which takes a function on the edges and maps it to the function on the vertices just by summing the values over the edges which are adjacent to the vertex. And this is the adjoint. So we see here that, my field is h, so this quantity only depends on this d star epsilon. So the idea is now to minimize the right-hand side in epsilon and satisfy the constraint that d star is some function that you fix. Okay? So a long story, okay, it's actually a short story. So a short story is that d star d is the Laplacian, is the graph Laplacian on your graph. So its inverse is just the green function. So if you plug all of that, if you choose epsilon to be, you fix a function on the vertices which is called m, and now you choose epsilon 0 to be this quantity, which is the gradient of the green function of the inverse Laplacian times your function. If you plug in this to this bound, you get the following thing. You get that now if you look at the variance of any vector of numbers on the vertices times your height function field squared, that this is smaller than the green function evaluated. Okay, the sum of green functions evaluated at every vertex times these masses m. So this is called the Gaussian bound. This is called the GFF bound on the variance. So it's a very simple problem, so we are surprised that this has not been known in this generality before, and somehow it fits the general conjecture that all height functions should be like GFF. Okay? But this is only an upper bound. And the difficult thing is to get the lower bound, which is like a GFF. So we don't get that because we don't control this part that we subtract here. It's not clear what that is. But up to an upper bound, everything fits very well in the picture. So how do you get, okay, this is saying something only about the height function model. So how do you get, so this is my last slide. So to get this upper bound, we really, we optimized in the way we choose this epsilon. And we choose an epsilon which is somehow a harmonic function, okay? It's a gradient of a harmonic function. And it actually minimizes, here we use the fact that harmonic functions minimize the Dirichlet energy, okay? This inner product of epsilon with epsilon is sometimes called the Dirichlet energy of a function. So harmonic functions minimize the Dirichlet energy, that's why it's best to choose to make a choice like that, and then we get the bound in terms of the green function. But this formula that we have, in the beginning it works for any choice of epsilon. So you can choose now an epsilon or a path. So you look at 2 points far away on the lattice, 0, 0, and n0, and you choose a path of this order, or these chi's in between them. Okay, and you call this path P. And you apply the formula for the variance in this case. Okay, so this is the formula. It's the same formula as before, but applied to this choice of epsilons. That the epsilons are 1 on the path and 0 everywhere else. So it tells you that first of all, this thing is a non-negative number. It's the variance of the height function. And then you have a difference of these two quantities in terms of the spin model, but we just proved it's smaller or equal than log n. But the point now is that the length of a path is much larger than, okay, so this proof is, I don't have an intuition for these steps. I mean, these steps are just there. You can make them. They are very easy. So we prove this upper bound for this quantity, which is log n. And now if you divide this quantity, you divide all terms here just by n, and then take the limit. On the right-hand side, this goes to 0. This is larger or equal than 0. So you get that the limit of this difference divided by n is actually 0. which actually tells you that you have some identity for correlation functions in the spin model. So we have not found any such identities before in the literature. So at any temperature in the XY model or any continuous spin model, you have an identity of this type. And now if you plug it back to this formula, and only now you use that the left-hand side actually diverges, because that's the localization, you get that the following sum of some type of two-point functions is infinite. So it's the same sum as here, but I multiply everything by I. So this one is always finite, and this one is infinite. Actually, we can prove that if and only if the height function is delocalized. So this is a proof that there is a phase transition, because this is just a two-point function of some observable of the system at 2 points which are far away, at distance I. And you clearly see from this formula that it cannot be exponentially decaying. If this was exponential of I, then this sum will always be finite. This sum is infinite, so it means that there must be slow decay of correlations when the height function is delocalized. And this is a proof. So the proof is just these 2 slides, okay, 3 slides, sorry, using duality. And it's sort of, it is, when you think about it, in the proofs that we had 2 years ago, we used some different representations of the model, which are called graphical representations. But if you look at the duality picture, it's an exact identity between 2 models. So you must be able to use it to conclude that if one of them undergoes a phase transition, then the other also undergoes a phase transition. But there was no such proof, but now there is a proof, and it's quite simple, and that's our paper. And in that paper there is quite a bit more results than only this. Okay, so thank you.
Thank you very much for the nice talk, Martin. So are there any questions?
Excuse me, you start with a very general formula, and then you make some step with model. Can you just maybe I missed something? Can you repeat what is generality of the result? So it should be very general also, right?
So that's a good question. I don't want to give the specifics of the generality, but basically, for this fact that delocalization implies a BKT transition, it works in any generality people are interested. So as long as your potential on the spin size is twice differentiable, which is, okay, it is an assumption, but people almost always make this assumption, you have this result. Okay, this is just a box to translate, and as an input we use the delocalization result of Pete, and that result has other assumptions on the potential of the height function. It's a very general result, it has some assumptions, but in the 2 most studied spin models, these assumptions overlap. So we can recover the results of Froelich and Spencer up to some weaker statements, but the phase transition is proved.
So it's a very nice argument, Martin. Thank you very much indeed. Do you get any closer to, I haven't quite understood, to the existence of a sharp phase transition, or is this only?
So that's a good point, because so in our first paper we do get a sharp phase transition for the XY model, and we wrote it and we're happy about it. And some experts that whose opinion I value were very happy about this sharpness. But then some other experts said that it's obvious. So it's in our paper, it's not in the paper of Froelich and Spencer, but there is a sharpness. There's exponential decay up to the critical point. At the critical point above you have power law decay. There is nothing in between.
And that's obvious?
It's, okay, you have to use a Simon leap inequality, which exists for the XY model.
Okay, so does that tell you then that in your height problem you have a sharp phase transition? So in the discrete Gaussian height model, do you have a sharp phase transition?
So this is a new paper by Pete. He has a paper on height functions themselves without spin models. and the integer value GFF fits into this framework.
Okay.
He assumes that you have a potential on the integers which is super Gaussian, which means that it's convex but whose second derivative is non-increasing. So it's some weird condition which for x, the potential x squared is satisfied. And he proves that in this case there is sharpness of phase transition, meaning that in the localized phase you have exponential decay of correlations, and above you have logarithmic delocalization.
So is it crazy to think that that might solve one of the problems of the de Bruijn states for the easing model?
Which is
well, that there is a sharp temperature above which or beneath which you have localization or delocalization of the de Bruijn interface, which is a height problem, of course.
So, yeah, I guess for the easing interface you need to make simplifications like the solid or on solid model, because otherwise it's not really a height function, because you can have like overhangs.
Well, absolutely, yes.
Yes.
That's where all the fun is.
Okay, I don't know, probably Peter is the better person to ask this question. I don't think it's been written for the question.
No, thank you. It's really interesting talk. It's my first time seeing the Bontragen duality used in this context. Is there any chance of using that duality to relate the surface tension or free energy of one model to another?
That's a good question. Yeah. Probably. Yeah, so my idea was that maybe you get interested, and I think there is lots of things still to do in here. In particular, the case of the Gaussian phi field, which is a self-dual model, and under that duality. And I don't know any result on that model which uses duality. I've never seen it used anywhere. I saw it in one paper, which is like a review paper of duality. And this is the most symmetric case, but somewhat it has not been used in that case, for example. So that idea.
Are there any other questions or comments? If not, let's thank our speaker again.
It's time to start the last session for today. Our first speaker is Professor Donju from Sofia University. He will present the topic, the disorder problem, an approach based on partially observable marking decision problem.
Good afternoon. In my talk, I revisit a problem stated by Sheref in his book Optimal Stopping Rules. And the problem is the following. In some probability space are given an observable random sequence, xi, and a non-observable integer random variable theta. Here I have written that it has a geometric distribution with parameter p, but in fact its distribution is a mixture of Bernoulli pi and geometric p distribution, as follows from this formula. Formally, yes, the random sequences consist of independent observation, but not identically distributed. Because if n is less than theta, then the corresponding distribution belongs to one family of distributions, say P0, and if n is greater than 0, to another family of distribution. Formally, Sheref introduces a measure, capital P pi, such that the probability of each event, capital I of the form, is given by the following formula. Here, capital P0 and capital P1 are both measures I have just mentioned, and we assume that they have densities P1 and P0. The problem is to find a stopping time with respect to the filtration corresponding to all observations, which minimizes the risk rho by tau. Sheref's solution to this problem is based on optimal stopping cruise in multi-gears. Here I developed an alternative approach to the same problem based on partially observable markov decision processes. This is a model with incomplete information which consists of the following elements. The first is the state space with 3 states. The action space with actions wait and stop. Observation space, this is the joint support of both densities. And the other elements of the model are transition kernel, observation kernel, running reward, initial distribution, and horizon. Formal definitions to these elements is given on this slide, but I tried to show a picture which describes the model better. This is an oriented graph. Its vertices are states of the state space, and arrows show transitions. The transitions depend not only on the state, but also on the action we apply. The black arrows correspond to the action wait, the red one to the action stop, and the green arrow indicates that state 2 is absorbing. The control process lives in states 0 and 1 and dies in state 2 after we stop. More info about it is available in the table here. In state 0, we observe the density P0, which means that the process is in this state before the disorder. In state 1, it is after the disorder. The disorder itself is the time of the first visit of the process in state 1. And for each action applied over time, we get some reward. The longer we stay in state 0, the closer we are to the time table, and this yields us a reward equal to 1. However, if we are in state 1, we have missed the disorder, and staying there, we only increase the difference from it. So, for staying here, we pay a penalty C, a positive penalty C. In order to avoid increasing losses, we have an option to stop and to go to state 2 where there is no penalty. However, if we are in state 0, we will lose all bonuses which we get in this state. And the point is that we don't know in which state we are. This is the reward if we apply the action wait. The action stop yields no reward. That is equal to 0. And here is the first difference of our approach with the optimal stopping framework, where the stop yields the low income and waiting actions yield nothing. Here we see that we accumulate our reward while waiting and receive nothing if stopped. Finally, the initial distribution is the same as in Chef. The problem is to maximize the expected total reward to the policy corresponding to the stopping time tau. The point is that we apply the action stop once, it identifies our policy. This calculation shows the total reward corresponding to the policy tau. We see that it is different than in Shiref. In fact, the second term is just the same, but the first is different. Also, it follows from this formula that the evaluation of the policy, which consists in instance of, that is the policy tau equal to 0, is 0. So we want to maximize the expected total reward, J tau P. The expectation is taken with respect to the same measure as in Shiref. To solve this problem, we follow a standard procedure of reduction of the problem with incomplete information to the problem for fully observable Markov decision process. This procedure consists of 3 steps. The first is to find a suitable sufficient statistic for the problem which plays the role of control process of reduced model. The second is to define the other elements of Markov decision process model with complete information, that is the rewards and transitions. And the final step is to solve the balance equation in order to find the optimal policy. Before to follow these steps, we note that the total probability formula implies the following decomposition of the total reward, total expected reward that corresponds to any policy tau. Here, on the right hand side, J capital 0 and J capital 1 are the expected reward if we know that we start from state 0 and 1 respectively. And here the second term, J tau 1 is 0 because if we know that we are in state 1, then the instant stop is the optimal policy, and we have seen that its evaluation is equal to 0. So it remains to find capital J 0. Here, the instant stop is certainly not optimal because the policy which recommends to wait one step and stop after that yields an income equal to 1. So this case needs special attention. And we start with filtration equations. They connect prior and posterior probability of both states 0 and 1 over time. Here is a mistake. I should be equal to 0 and 1, not 1 and 2. Here, this equation, I think they need not comment because they follow from the total probability formula and base value. The general theory recommends to use posterior probability of sum of the states 0 or 1 as sufficient statistics. But here is more convenient to work with prior and posterior odds given by these formulas. The point is that if we introduce the control process in the reduced model, capital Xn, by this formula, and we see that here capital Xn is a linear function of posterior odds, then Xn forms a Markov chain, which is given by this formula. This Markov chain is studied very well. There are a number of papers devoted to it. I will mention here the seminal papers of Fermat and Kester. And it's a real bonus to work with this Markov chain in our case. After we have found the control process, have defined the control process in the reduced model, it remains to calculate the reward in terms of this process. This is easy to do because in terms of posterior probability, the reward is given by this formula. This is a bonus equal to 1 if we are in state 0 times the posterior probability minus the penalty C multiplied by the posterior probability of the state 1. And it is a simple algebra to express R0 and R1 in terms of X. And because we have seen here that if we know X, in fact we know the posterior odds, and the sum is equal to 1, and a simple algebra allows us to find the following reward function in the reduced model. It remains to find the transitions of this Markov chain. In order to do that, we need the conditional distribution of xi given that xi-n-1 is equal to, say, to y. Here we make use of the following representation of the prior nodes in terms of x n-1, and similarly, making use of this calculation, we find this transition. In fact, this is the transition kernel in the reduced model. Now we define the total reward in the reduced model as the sum of the rewards till the time when we stop. The value function is the maximum expected reward over all stopping time tau, and this is the Bellman equation which satisfies capital V, the value function of the model. Here, the plus brackets corresponds to the action stop, and the expression inside brackets is the maximum income if we start with the action weight. And now we want to solve this equation, but before to do that, we make we give some pure information about the value function capital V. It is strictly positive in decreasing on some interval 1 y0. It is 0 if y is greater than 1 0, and the optimal policy recommends to stop immediately after capital Xn is greater than the threshold y0. Now we are about to solve Bellman's equation. To do that, we make some standard transformations to this equation. First, we multiply it by the denominator of the expression under the integral, this one. Make a substitution and introduce a new unknown function, capital Y. Then capital Y satisfies the following equation. To proceed, we recognize here that the integral is just Millin's convolution of right-shifted function capital U and transform density P1 by the deterministic function A. This is the well-known formula for such a transformation. However, there are two things to cope with in order to apply Millin's transform to this equation. The first is to understand when we can get rid of the plus brackets. And the second is to understand what to do with the right shift of this function. This is a right shift by 1 unit here. To answer the first question, we see that if C is equal to 0, we certainly can get rid of the plus brackets because there is nothing negative inside them. And the idea is to do the same if C is small. Of course, this is not correct, but our error will be small if C is small too. Thus we come to the following definition for symptotic solutions to Bellman's equation for small c as tends to 0. So we take a solution to the equation, to this equation without plus brackets, divided by the same thing to which we multiply the equation before, and take plus bracketed this solution. Nice thing is that the threshold is the same for both functions, for capital V and for capital V. It remains to understand what to do. By the way, I think that this is the most interesting case if C is small. I will not focus on this right now, but if I have time and there are questions about this, I will explain why I think so. And now we are going to apply Millin's transform to the equation without brackets, but we need one more thing in order to cope with the right shift of the function. We will be looking for solution to this equation in the set of Mayer's G functions. These are functions whose Millin's transform is such product ratio of gamma functions. Why? Because the following results holds true. A version of this analytical lemma in case of Laplace transform can be found in Lavrentiev-Ishabat's book on complex analysis. This is a lemma for the Millin's transform of composition of the two functions. And we need just the same because we have composition of the function capital U with the unit shift, that is the function x plus 1. This is the lemma for the Millin transform of composition of two functions. And the point is that this function J capital SU that corresponds to the unit shift to the function x plus 1 is a beta function. So this formula applied to our equation leads to such a transformation of the equation for capital U after we apply to it Millin's transform. And now, of course, Because to solve this equation, if we know capital A is means transform of P1, of the function of the density P1. If we apply to solve this equation for known capital I is a hopeless task. But we can do the following. To take some G function, then its mean transform will be product ratio of gamma function. And the same will be under the integral. And then this integral here is just inversion formula for G function. And the nice thing is that there are closed formulas for G functions in terms of generalized hypergeometric functions. So we can take suitable G function and find everything except the Millins transform of the density P1. So we can find Millins transform of P1, and if we are able to convert the Millins transform, we will find a density for which the corresponding G function is a value function for our problem. Thus, we will find a close solution to Bellman's equation in some cases. 5 minutes, I think.
It's time to say thanks to Professor Donji.
One more thing. It is important to answer this question. Is it possible? Because this approach seems to be very complicated. So it is, can we expect real result applying this approach? I'm optimistic because in Prudnikov, Marichev reference book on special function, there are more than 100 pages with tables for G functions and their Millins transform. And more, a similar approach I was applying maybe 10 years ago to get the following result. If we have a sequence of ID random variable with beta 2 distribution with parameters A and A plus 1, then the stationary distribution of the same Markov chain which arises in our problem is Pareto with parameters 1 and A. And I don't know, is it possible to get the same result in a different way? So maybe we will find solutions to Bellman's equation for this problem in a closed form too, which is really nice.
Thank you very much. Questions or remarks? I would like to make a comment then. In your last equation, this Pareto appearance of this Pareto distribution maybe comes from the fact that it can appear as mixture of gamma and beta is related with these distributions. Maybe this
you
is
think that this Markov chain,
the last equation.
This equation?
Yes, in the last equation. You say that xn is Pareto. Am I right?
The stationary distribution of this chain is Pareto.
The stationary.
The stationary distribution.
Okay, thank you. Thank you very much. Our next speaker is Professor Marusa Boshko from Sofia University. She will speak about, let me see, escape from extinction with the composable multi-type Sebastian branching process.
So, hello everybody. Thank you for thank you the organizers for inviting at this highly esteemed conference. I will present a talk about the escape from extinction, which is a problem that is tackled by means of a branching process, namely the Sebastiano branching process, and it is a joint work with my PhD student, Kalyan Vitanov. So the content of the talk is as follows. I will start with the model introduction, then we'll state some theoretical results, which are actually the results concerning the number of mutations from two class of types, which we define in the next slide. Next, the probabilities of extinction and the time until first successful mutant. So, the most important is to say from the very beginning that this modeling is closely related to the cancer development disease. This means that in a typical branching process model, we are trying to introduce a probabilities of mutations in order to model the evolution of this disease. So I will explain the specifics of this model, which is driven by the cancer development, and also what we obtained are some numerical methods which are developed for the systems of integral equations, which we by means of which we studied the characteristics I already mentioned, and then I will end up with several experiments to illustrate our methodology. And because of the modeling purposes, we consider that we have a space of types of the cells. Maybe it is written particles because this is a general notion in the branching processes, but actually from time to time I can say I can speak about cells. So the space of the types of the cells is denoted by W, and we have a finite number of types, numbered from 1 to n, and what we suppose further is that we have two non-empty subsets of W denoted by W0 and WE. So that WE is W minus W0, and this E comes from emit. That is to say that, as you may see in this flow chart, this is the aim of this flow chart is just to illustrate the main idea of this modeling. That is, the types in this process, they are decomposed in W0 types, which we conditionally denote from 1 to k, say. And you see that they are connected, or they are communicate to each other. And other states from k plus 1 to n, they form the class WE. And as I said, E comes from emit, and this means that you can see that all these types from WE could communicate or could produce cells. Namely, these are the mutations or the cells from the class W0. So on the edges here, you will see the probabilities of mutation. So I will continue now with the short definition of a single type Sebastiano branching process, because it is the basic process. The Sebastiano branching process is an age-dependent branching process, meaning that we have a dependence of offspring of each particle or cell on its age. So we have mainly two characteristics which are driving the behavior.
Recording in progress.
Which?
Just keep this cross.
So here. Okay. Oh, sorry. So we have two main characteristics which are driving the behavior of such processes. This is the distribution function of a lifetime of each particle, denoted by tau, and the offspring distribution of the random variable nu, which is denoted by pk of u. They are sum up to 1 and...
Recording in progress.
Sorry, again. So, and these probabilities are these conditional probabilities to have k offspring, provided that the particle is of h tau less or equal to u. So this is actually the single type Sebastian branching process, and having in mind this definition, the multi-type process is as follows. So for each type of particles or cells, we connect a distribution function of a lifetime denoted by gi of t. This is a small remark that tau I do not depend on population size and the distribution of particles among types, and also they don't changing during the process. They are defined at the beginning and will be the same during the whole process. And one and the same for all particles from type I. And okay, for the number of offspring, we have respectively these probability generating functions, Fi, U, S, with these probabilities. Again, we have the same assumption about the characteristic mu I, and moreover, what we assume is that the descendants of type I, which is from class WE, can be of any type J in the space of types. However, the types from the class W0, they can only be from the same class W0. And we speak about mutation when a particle of type I produce a mutation, a particle of a type which is different from I, and that we call mutation. And the probability that we have such event is denoted by Uij. These probabilities, they are summed up on J to 1, and moreover, when there is not a possibility to have a mutation from I to J, it is natural to suppose that this probability equals to 0, and so our process will be denoted by this vector z of t, where each component means the number of particles of corresponding type existing at time t. And I will skip these remarks. The theoretical results we obtained for this model are connected to the number of mutations from the class WE to the class W0. And we denote by I, W, E, M, T, the number of particles produced by a particle from class WE towards a type M from the class W0. So we are tackling this problem by use of PGIF, which in this case are multivariate PGIFs, which are actually defined in this way. So this is the expected value of this product. And the S, the bold S here, is actually the n-dimensional vector, which corresponds to the number of types. And because we are interested in the class W0, not all of the coordinates of SR participate in this generating function. And actually this function compactly contains information about the number of mutations from WE to W0 types that have occurred until time t, provided that the process begins at t, at the beginning, with one particle of type I. And what we established for these probability generating functions is this system of integral equations. You see, for all I in WE, we have this system of integral equations. The functions here are supposed to be known, and for I in the class W0, it's naturally that this PGIF equals to 1. Moreover, we also consider the number of mutations from types in WE to types in W0 from the whole process. So this, again, the random variables which are used to model this quantity are denoted by IWEM. And actually these are the limit of the previous random variables when t tends to infinity. So we denote these PGIFs. Again, this is a multivariate PGIF, which corresponding to the process starting with one particle of type or cell of type I. And because of the one-to-one correspondence between random variables and the PGIFs, we have that these functions, HWEIFS, are the limit of the functions which we received in the previous step. And this way, we established a system of integral equations similar to the one from theorem 1 for these PGIFs corresponding to the number of mutations during the whole process, not up to time t, but to the whole process during its survival. So this is when I is from the WE class, and if I is from W0, then again these probability generating functions are equal to 1. And as I said, we are interested in the probabilities of extinction, which again are indexed by the number of the initial type. So we express these probabilities in this way. The sum of all existing particles of each type at time t should be equals to 0, provided that we start with one particle of type I. So this is the probability that the process will extinct by time t, provided that started with one particle or cell of type I, and these are the probabilities for extinction, or we call it also ultimate extinction, provided that the process starts with one particle of type I. And for the QI, what we obtained is, again, maybe you notice already that this integral system of integral equations, they are following more or less one and the same pattern, and we will see a little bit later. So we have this system of integral equations for the probabilities of extinction by time t. And also we have the system, if I is from the class of states of types WE, and for E in the class W0 we have this system of integral equations. And in a similar way, but if we suppose that each particle within the class WE be either subcritical or critical, then for all types in WE, we obtain this system of integral equations where Q is to be understood in the same manner as S from above. And the last characteristics which we can characterize in terms of this model and is interesting from the cancer modeling is the time until first successful mutant. So successful mutant for us will be this one, which will gives rise to a trajectory which will go to infinity, or in other words, this mutant which will escape extinction. And this random variable is denoted in this way, TW0WE, and it might be equal to infinity as the event that no successful mutant occurs during a process beginning with one particle of type I. So this random variable has its values at the interval 0 plus infinity. And probably it is interesting to comment these results about the distribution of the time to appearance of the first successful mutant. So you see that these probabilities are expressed in terms of the probability PGFs that we already introduced, and which are characterized in terms of an integral system of integral equations. And also we are able to find the conditional expectation of this variable on the condition that it is finite, and it is again expressed in terms of quantities that we already address. So as I said, this model is closely related to the application, and this is in the cancer modeling. One of the prominent traits of cancer is its ability to mutate and or spread through different parts of the human organism. And in order to attempt modeling this disease with branching processes, it is necessary to consider candidates or candidate, which is should be a multi-type branching process, which allow mutations between different cell types, and we denote the cell types, as I already mentioned, by W. And here is another flow chart, just to draw your attention that it might be interesting to have in mind such a particular case of Sebastianov multi-type branching process, where type K here is reachable only after mutations leading to type 1 to K-1 occur. And subcase of special interest arises when type K is the only supercritical type. These types in the class WE can be used to model an existing badly adapted population approaching extinction, while the mutation path towards type K provided by the types within W0 leads to possible escape from extinction. And So the real situations when such models appeared are when during the administration of a medical treatment of cancer for cancer cells to mutate so that they become resistant to the treatment or to spread to a part of the human organism that is not affected by the treatment. And to capture this feature, we naturally divided the whole space of types into two classes. I will skip the other remarks here, and generally speaking, mutation from well-adapted states, which are in the class W0, towards less adapted states from WA is not likely, and thus a candidate branching process needs to be able to provide theoretical results in the context of decomposability of a branching process. And upon successfully identifying the different cancer cell types, the immediate question of interest is what is the probabilities of the process to become extinct, and in relation to the initial conditions, namely the number of and the type of the beginning cells. In other words, the values of Qi of t and Qi. And successfully calculating these values may provide useful insight into the choice of medical treatment to be applied. Other important questions are related to the time until occurrence of the first successful mutant. You see in theorem 5 already these quantities, they are again characterized in terms of PG-ifs. So I will skip this. So the decomposable multi-type Sebastian branching process model captures the above mentioned features of the evolution of cancer disease, and as shown provides a theoretically and computationally manageable framework for obtaining many quantities of interest. So there are two drawbacks. The first one is that all possible cell types need to be specified at the beginning of the process, and the second main drawback being the nature of the practical procedure of estimating the parameters of the types. Despite these drawbacks, this model provides a good starting point for modeling cancer and other phenomena in continuous time. And as I said, concerning the numerical methods, we noticed that the systems of equations exhibit a common pattern in the structure of their expressions. So we have a part, integral part, so this is actually the table. But I wanted to say that we have an integral part where the second argument of function fi is commonly denoted by c. So all the equations that appeared in the systems could be summarized in this table, where we introduced as a general notation Li for the quantity we are trying to find. For Ai of t is this part, which is in terms of the distribution function of a lifespan, and this is the integral part, which is commonly denoted by Bi of t. So also, we included here equations which are concerning the PGs of the process itself, and they are also in this scheme. So, for all these equations, we develop a numerically procedure which consists in these steps. We initialize the the stated t equals to 0, and for every I that participate in the system of integral equations, we compute the corresponding initial point Li, which was the first column in the table, and then for t equals k h, where k is 1, 2, and so on, and h is the chosen step size. For every I that participates in the system of integral equations, we compute this Li at step kh. And the experiments which are done in this setting, so we consider that we have such PGs for, so we consider 6 types in our process. These are the PGs which are controlling the reproduction of each type, and we suppose that first 1, 2, and 3 types are in a class W0, and 4, 5, and 6 are in WE. And note that the types in WE, so this column here is corresponding to the expected number of offspring. So we deliberately chosen the types 1, 2, and 3 in 4, 5, and 6 in the class WE, so to be subcritical, so that the conditions of theorem 4 holds. And these are the probabilities of mutation, and the lifespan distributions for each type are supposed to be exponential and log normal with such parameters here. So, if we take t equal to 250 and the step size hb 0.1, then depending on the initial type, we obtain for the probabilities of extinction by time t equals to 250 steps, that these probabilities are as follows. So it was maybe interesting to say that type 1 and type 3, in terms of expected offspring, actually are supercritical types. So when we start with the corresponding type I, you see what are these probabilities. And as I said, they are characterized in terms of the PG HWE of I. And these are the values of this PGF. And so here is the evolution with T of the probability of extinction of a process starting with one cell of type I. So you see that Q4, where for the type 4, it was a subcritical type. So you see here that this probability is different from the others, which correspond to types Q2, 6, and 2, 6, and 4, where these these probabilities are very fast, close, tends to 1, and this is the respective evolution of the PGF of the number of mutations by time t, again with time t for 250 steps. And then if we want to see the convergence for these 3 trajectories of Q of when started with 4, 6, 5, and 6 type of initial particle. So we see that we have such a convergence of the PGF and the value of the function Q4. In this case, this is for the initial particle of type 4. This is for initial particle if the initial particle is of type 5 and if it's of a type 6. So these are the general references used. These are the classical books by Harris, Atreya, Ney, Peter Jagers, Charles Mott, Kimmel, and Axel wrote. And I would like to say that this research started actually with this publication by Serra and Haku, Dynamics of Escape Mutants, where they introduced a very simple model only with 2 types and in a discrete time, namely they used Bien and Galton-Watson process. And also we use some of the approaches developed by Ivasa, Minchor and Novak in these 2 papers. Also, I mentioned here the literature that is connected to cancer modeling, and here are all the papers which we published with my co-authors Vitanov and other 2 my PhD students, which are devoted to all this modeling, because this is the last expansion of the model, and the results which are included in this presentation are published in these 2 papers by Kalyan Vitanov and myself. So, thank you
very much for in order to prepare this talk. Are there any questions? Remark?
I just wanted to ask, what's the cancer evolution interpretation of the types W0 and WE? I missed it at the beginning.
So, WE are so-called subcritical or critical types, such that they correspond to the types which are less adaptive, or these types which are resistant or are not resistant. They are affected by the treatment, and sooner or later they will become extinct. These are WE. And in W0 or W0, possibly are these types which emerge from W0 through mutations, but they are bad, or they are very well adapted to the treatment, and at some moment they become resistant, so a new treatment should be applied in order to stop this event escaping from extinction, because escaping from extinction in terms of a cancer is very bad.
Thank you.
Thank you very much. Other questions or remarks? Okay.
Have you any real data for cancer, from cancer research?
Actually, we have some data from our center at the hospital, oncological hospital in Sofia, about one particular type of cancer, and breast cancer, namely, and what we are trying to extract from this information, because it's not very informative, is to see how many times or how are distributed the different cases according to the appearance of re-emerging, or according to the appearance of successful mutants. So we have at least 5 such cases where this disease occurs again. So probably we will try to extract more information just for this modeling, but we'll see.
Thank you very much. Other questions or remarks? Okay, let us say again thank you to Professor.
Okay, so I would like to thank the organizers for organizing this conference and for giving me the opportunity to present my research here, which is based on a joint work with my collaborator Arnaud Roussel. So the topic of my talk is settled in the area of random graphs, and here's a short outline of my talk. So I will start by giving a motivation for the random graph models under consideration. And in this talk I will focus on two models of long-range calculation. One is a long-range calculation on the lattice, and the other one is called the random connection model. So here I will give a definition of these models and recall some results from the literature. And subsequently I will present my research on this model. So the new thing in our approach is that we did an extreme value analysis on these models. And here I'm going to present some of the results that we obtained. And I won't go into any proof details or technicalities. So here I start with the motivation for these models, which basically comes from the small world property observed in real-life networks. And here's a mathematical formulation of this small world phenomenon. So assume we are given a graph G consisting of a set of vertices V and a set of edges denoted by E, and we assume that the edges are undirected. And now assume that we are given a random graph, so later I'm going to specify the randomness, but for now assume that it's just given a random graph with vertices, n vertices labeled by x1 until xn. And now you look at the so-called graph distance or graph theoretical distance between two vertices, defined here as the quantity d of xy, which basically counts the number of edges in the shortest path between x and y. And then the formulation of the small world property is that the probability that the maximal graph distance in this random graph is less or equal than log n goes to 1 as n, which is the number of vertices approaches infinity. So in terminology, we would say that with high probability, the graph distance grows at most logarithmically. And this is the small world phenomenon. And this will be fulfilled in the random graphs under considerations, which are basically random graphs that have geometry. Therefore, they are also called random geometric graphs. So I will speak about, as I said, the random connection model, which is defined on the continuum RD, and the long-range calculation, which is defined on the lattice set D. So these models are basically analogous counterparts. One is defined in the continuous space and the other one in the discrete space. So therefore, in this talk, I will call the first model continuous long-range calculation, and the second model I will refer to as discrete long-range calculation. Okay, and here's the definition. So I start with discrete long-range calculation, which was introduced by Schulman in 1983. So in this random graph, the vertex set is given by the d-dimensional integer lattice, and the edge set is constructed randomly by basically saying that we connect an arbitrary pair of vertices u and v with some probability that only depends on their distances, here denoted by g of u minus v. And we do this independently for every pair of vertices. So most of the works on long-range calculation classically assume that this probability has a polynomial decay in the distance, which means it asymptotically behaves like the Euclidean distance of u minus v to some power minus alpha, which is a positive constant. So the model is basically parameterized by two constants, which is d, the underlying dimension, and this alpha, which controls the probability. Okay, here I put a simulation of this random graph in dimension 2 with the value of the exponent alpha equals 3.9. And if you look at this picture, then you will see that there are a lot of short edges and only a few long edges. This is how the random graph would look like in dimension 2. Yeah, as I said, so the model is parameterized by D and alpha, and here are some first preliminary results about percolation behavior in this model. So percolation is about the existence of an infinite connected component, and it is known that in this graph, well, if alpha is less or equal to D, then every vertex is connected to infinitely many other vertices, almost surely. This is a quite easy application of the Borel-Contelli lemma. So in this case, the graph would not be locally finite. And otherwise, if this constant alpha is larger than D, then the graph is locally finite, and there also exists an infinite connected component or cluster. So in dimension 1, this is only the case if alpha is between 1 and 2. As soon as this alpha is larger than or equal to 2, then there's no infinite cluster. And in dimension higher than 2, this is true for every alpha larger than D. Okay, so these are some first order results. And now the results regarding the small world property about the graph distances. So essentially the works on this model have revealed that there are 5 distinct regimes of typical behavior for the graph distances, which is according to the value of alpha and D. So basically you have a phase transition in this model. The first phase is alpha less than D, then alpha equals to D, alpha between D and 2 times D, and alpha equals to 2D, and alpha larger than 2E. And attention to each of these cases has been devoted separately. So here I put just a few authors that have studied these cases, so there has been a lot of attention on this case. So these are the most recent references that I'm aware of. And also it is mentionable that in all of these works, typically they assume that nearest neighbor edges are present with probability 1. So if 2 points are at distance 1, they're connected almost surely. This is what these works typically assume. Okay, then here are the precise results regarding the graph distances. So here I start with the case alpha less than D. And the results stated in this way that you look at the graph distance between the origin and x, and at the corresponding behavior if the distance between the 2 vertices, the Euclidean distance, goes to x. And in case alpha less than D, the statement is that with high probability the graph distance is bounded by this constant d divided by d minus alpha. So in particular, a small world property is fulfilled in this case, and sometimes this is also called the ultra small world property, because here you have boundedness by a constant. And so the behavior changes if alpha is equal to d. Then in this case, it is known that the graph distance can be compared to the logarithm of the Euclidean distance divided by the log of the Euclidean distance with high probability. So here the small world property is still fulfilled, but it's not ultra small as before. And then we have the case alpha is between d and 2 times d. So here it has been shown that the graph distance can be compared to constant times the power of the logarithm of the Euclidean distance. And then we have the case alpha equals to 2d, which is actually the most interesting and most difficult case, because here the corresponding results are only proven in dimension 1. And as far as I know, there is a preprint on this case, but it has never been published, so I don't know if the proof is actually complete or not. But basically, in this case, the result is that the graph theoretical distance can be compared to a power of the Euclidean distance. So starting from alpha equals to 2d, the random graph basically doesn't fulfill the small world property anymore. And then we have the last phase, alpha larger than 2d, and here it is known that with high probability the graph distance grows at least linearly in the Euclidean distance with high probability. Okay, so these are the results of the graph distances, which are basically used in order to characterize the geometry of the graph. And another way of doing this is by looking at the behavior of the simple random walk and classical questions regarding recurrence and transience. And this was initially done by Noam Berger about 20 years ago. And his work on the random walks essentially also revealed that the behavior depends on the value of alpha and d. And the precise results are as follows. So in dimension 1 and 2, if alpha is larger or equal to 2 times d, then it's known that the random walk is almost surely recurrent. And in every dimension, if alpha is between d and 2 times t, then it's known that the random walk is with probability 1 transient. And as you see here, there's one open regime, namely if the dimension is larger or equal to 3 and alpha is larger or equal to 2 times d. And actually here in this case, it has been known that, so it's been open ever since. So the proof, there's still no proof in this regime, but it is highly conjectured that the random walk will be transient in this case as well. Okay, so these are some results on discrete long-range percolation, and now I turn to the continuous model, which was initially introduced by Matthew Penrose in 1991. And the idea is basically that you replace the vertex set by the points of a homogeneous Poisson point process with some intensity constant rho. So that's the only difference between the two models, because given the vertex set, now the edge set is constructed as before by saying that an arbitrary pair of vertices is connected with some probability g that only depends on the Euclidean distance. And now this g, basically you can take an arbitrary measurable function which is symmetric in this sense and satisfies this non-trivial integrability condition. And again, you do everything independently for all pairs of vertices. So this is just a heuristic construction of the continuous model. There's a more formal construction by means of a marked Poisson point process, but I won't go into the details here. Essentially now you have a model which is also parameterized by this constant rho, the intensity of the point process, and by this function g, which is also called the connection function. So here's a simulation of this random graph. If this constant rho is equal to 0.3, and if we choose a probability with check as a polynomial decay as before with the value alpha equals to 3.9. And again, as you can see in this picture, you have a lot of short edges and only a few long edges. And actually here, for example, is the longest edge in this graph in the simulation. Yeah, so basically for this model, regarding the percolation, it was proven by Penrose that you have a phase transition which depends on the value of the intensity constant, in the sense that there exists an intensity, so-called critical intensity rho c, which is non-trivial and finite, such that if the intensity of the underlying point process is below this critical intensity, then there's no percolation with probability 1. And if this intensity is above the critical value, then there is a percolation with probability 1, and the infinite cluster is unique and locally finite. So under this assumption that you have an infinite cluster, for example, you can also study the recurrence and transience of a simple random walk on this random graph. And as before, one may choose the connection function to have a polynomial decay in the distance. And this is what we have done with my collaborator Arnaud Roussel 2 years ago. So we fix the Euclidean dimension and this connection function with polynomial decay, alpha is larger than d. And then we basically have proven that here in this model we obtain the same results as in the discrete model for the random walk. So namely, if d is equal to 2 and alpha is larger than 2 times d, then the random walk is recurrent with probability 1. And if d is larger or equal to 2 and alpha is between d and 2 times d, then the random walk is almost surely transient. And if you remember, in the discrete case, there was one regime which was open, namely the case d larger or equal to 3 and alpha larger or equal to 2d. So we are also able to provide results in this regime, namely that you indeed have transients of the random walk. However, we do have a small side condition, namely that the underlying intensity of the point process has to be sufficiently large. But if we can ensure this property, then we can also prove that you have transients in this regime. Yeah, so these are basically the results about the behavior of the random walk, and we have also looked at the graph distances in this model. And essentially here again we obtain the same type of results as in the discrete model, namely that we have phase transition according to the values of alpha and d. And we have exactly the same phases as before. So alpha equals to d, alpha between d and 2 times d, alpha equals to 2d, and alpha larger than 2d. Yeah, and we actually get precisely the same behavior regarding the graph distances as in the discrete model in all of the regimes. But now the way you state the results are a little bit different because, so you look at the graph distance between 0 and x, but since the vertex set now is a random set, you have to ensure that 0 and x are points of the realization of the Poisson point process. So the results are stated in a way that you condition on the event that 0 and x are part of the point process. And under this condition, for example, if alpha equals to t, you can again prove that the small world property is fulfilled and that the graph distance between 0 and x can be compared to constant times the logarithm of the Euclidean distance divided by log of the Euclidean distance. So the same type of results as in the discrete model, and this is also true if alpha is between d and 2 times d, and alpha equals to 2d and alpha larger than 2d. So these are the results on the graph distances, and as you can see in most of the aspects, the two models behave similarly. And now, regarding the most recent research that we have done, so the model is called long-range calculation. In particular, you can have long edges, and our motivation was the following question. So we asked, how long can an edge possibly be? And this is a mathematical formulation that we chose for this question. So now we fixed just a generic notation for both random graphs for the discrete and the continuous model. And now we fixed also an arbitrary general connection function for the edges denoted by G. And now we fix a ball of radius n, a so-called observation ball. And now we define this edge set EBN as the set of all edges with at least one endpoint inside of this set Bn. And we are interested in the asymptotic behavior of the length of the largest edge length in this edge set, so which is defined as the maximum over all edges inside of the set EBN of the length of this edge. And basically, so we're interested in the behavior of this quantity as the volume of the ball, or this quantity n goes to infinity. And this is essentially a question that falls within the scope of extreme value theory. And in extreme value theory, it's natural to study the so-called sum of exceedances. So now we define an auxiliary random variable, this Wn of Rn. So Rn is just some threshold function, and this random value Wn basically counts the number of vertices which are endpoints of an edge that is longer than this threshold Rn. So basically count how many edges are longer than Rn, and studying the maximum basically boils down to showing Poisson approximation results for this random value W of n. So basically our idea is to show that this sum here converges to a Poisson distribution, and from this you can derive properties on the asymptotic behavior of the maximum. Yeah, as I said, we fix now more general connection probabilities, and we in particular looked at three classes of connection probabilities. The first class, which is the widely studied class of probabilities with polynomial decay, and then we also looked at a second class with function of exponential decay. And then we looked at a third class under which the edge lengths are by default bounded by this constant m, at which this connection function has a power law behavior. So these are three classes of functions for which we studied the problem, and here are the results that we obtained. So here start with the functions of polynomial decay, and I will split the results into the continuous model and the discrete model because it actually turns out that there are differences for these two models in the problem that we studied. Okay, so here I start with the continuous model because the results we obtain for these models are actually a bit nicer, even though they are more difficult to prove. And here we essentially showed that the edge length properly normalized by some scaling sequence an converges in distribution as n goes to infinity to a Fréchet distribution with parameter alpha minus d. So you get a heavy-tailed extreme value distribution in the limit. And in the discrete model, we showed the same. However, we were only able to show this if this constant alpha, which controls here the probabilities for the connection, is between d and 2 times d. That you again have the same Fréchet convergence as in the discrete model, but only under this condition. And actually, it turns out, if alpha is not between d and 2 times d, then for the discrete model, this result is not true anymore. And we were able to disprove this in dimension 1, and it is following result that we obtained in this case. Okay, so if alpha is unequal to 2, then you get the convergence that you expect as in the discrete model, the Fréchet type convergence. And if alpha equals to 2, then you have, so to say, a singularity, so you have a singular behavior in the sense that now if you scale this edge length by the same scaling sequence, it does converge in distribution. However, the limit that you obtain is not a Fréchet distribution anymore. In fact, you obtain in the limit a random variable which is almost a Fréchet distribution in the sense that it's heavy-tailed, so its distribution function at some point r is the same as the distribution function of the Fréchet distribution if this argument r is larger than 1/2, and if r is less than 1/2, then this distribution function has actually a more complicated expression. So you don't get a Fréchet distribution anymore, but something that is almost a Fréchet distribution. So in order to make this maybe more clear, just a short visualization of this result. So here I plotted the distribution functions of the limit that you obtain. So in the black line you see the limit for the continuous model, and in the dashed blue line you see the limit for the discrete model. So as you can see, they're almost the same, however, there's a small deviation around the origin. This is basically, so to say, a behavior that we didn't expect. And also what is mentionable here, we also studied this problem in case that you look at directed edges, and in such a case, such a singular behavior does not occur. Okay, so that's the result for probability with polynomial decay. And now here we have a result for the probability with
recording stopped.
With exponential decay. Here again I start with the continuous model, and there we essentially showed that you can properly normalize the edge length. So additionally now you have to introduce the scaling sequence, centering sequence En, and the scaling sequence An, such that the normalized edge length converges in distribution towards the Gamma distribution as n goes to infinity. And the same is true also in the discrete model, however, there we were only able to prove it in dimension 1 and not in arbitrary dimension. How much time do we have? Okay, I will sit up here. Yeah, so these are the results for probability and exponential decay, and now the last case when you have a probability where the edge lengths are bounded by this constant m. And here we showed a convergence of Weibel type for the continuous model in the sense that we can properly normalize the edge length, center it by this constant m, and scale it with the scaling sequence An, such that this random variable converges towards a Weibel distribution as n goes to infinity. And again, there's a difference between the continuous model and the discrete model, because in the discrete model, if you use the same normalization, this thing goes to minus infinity with probability 1, so you don't get the same behavior for the edge lengths in this case. Yeah, okay, essentially, so these are the results in this case, and I think that's everything what I wanted to talk about today. So my talk has been based on these 4 papers, 2 of which are already published, and 2 are currently submitted as a preprint.
Thank you very much for the nice talk.
Thank you for the nice talk. I think you said that in the discrete model you keep the nearest neighbor edges.
Yes, so that's the studies on the graph distances.
Right.
Yes.
And I guess that in the continuous model there is no reasonable way to do the same thing. But at the same time the results on the 2 look kind of similar.
Yes.
So could you maybe comment on why don't we need maybe a similar net in the continuous model to have the same results?
Yeah. So essentially, I also said that the way you state the results for the continuous model are a little bit different, because here you have to condition, for example, on the event that 0 and x part of the Poisson point process. And in the first statement, you essentially only provide the lower bound on the graph distance. So lower bound, actually, you don't have to assume that the nearest neighbor edges are present. You essentially only need it for the upper bound. And here, if you look at the statement for the upper bound, here you condition on the fact that 0 and x are a part of the infinite cluster. And essentially, this is useful because you need the graph to be connected. Otherwise, in general, you can't find an upper bound on the graph distance.
But in the infinite component, you can also have some very long edges, so the shortest path could be just a few very long edges.
Yes, the shortest path, but you look at the yeah, but if you put the nearest neighbor edges, then the shortest path could still be shorter.
Thank you. Other questions? Okay.
Yeah, it's a very nice talk. I'm kind of, this is all new to me. I understand roughly why alpha equals d is a critical point where you get a change in behavior. But what's so special about alpha equals 2d?
So there are a lot of special properties about this model, but so I can, for example, give a heuristic argument for this. If you're familiar with alpha stable distributions, you have the index of stability, which is between 0 and 2, and it is always known that alpha equals to 1 is a very special case, because so the distributions are defined for characteristic functions, and for alpha equals to 1, the characteristic function is a more complicated expression. And in some sense, there's an analogy in the sense that alpha equals to 2d is the same as alpha equals to 1 for stable distributions. And somehow it has turned out in the literature that it's technically also the most difficult case.
Okay. The time is over. However, are there any other questions, or you prefer to ask them during the break? Okay, I also have questions as far as I work in a similar topic, but I will ask them during the break. Now it's time for the next speaker. This is Alexander, as far as I know.
Okay, so I want to speak about some sort of side result which came out of my PhD thesis, which I conducted at Paderborn University, about this inverse first passage time problem. But for this talk, I decided to start with the particle system of this talk here. And to start right away, in this particle system, we will always have distribution of positive real numbers given by this positive random variable. And then we have this natural number n, which is associated to the amount of particles. And for these parameters, we look now at n independent copies of this psi, this random variable, and then we look at the n order statistics. And we see these order statistics as random time points at which we follow the following scheme. So we start with n independent bounding motions, and at every time point tk, we remove one of the bounding motions, namely the one with largest absolute value. So it's very simple. We have these n bounding motions. At every random time step, we just pull out of the system the one with largest absolute value, and between this we have the random motion, the bounding motion independently. Okay, and of course it's nice to illustrate this. So just for the notation, we denote AT as the particles alive up to a time t, deterministic time t. And to illustrate this, here is some simulation of the process. So for n particles, and now the distribution is a uniform distribution on the unit interval, and we have here the three-order statistic, and you see we start with three rolling motion. This is one is killed here, this second one killed here, the third one here, and we end up with a zero set of surviving empty set of surviving particles. And what we are interested in now is when the particle number grows large, so the initial particle number. So here, this was a spoiler, but for example here, when we just increase the particle number to 40, we already see some pattern that the particles are somehow prevented to being too large. And if we increase this more, then we get this picture. So somehow there is a boundary evolving over which the particles cannot go over anymore. So, and to understand what we see here, I want to show you the following heuristic. So if we could assume, if we just suppose that we can assume that for large particle size, we have that the maximum particle of the system is some deterministic function, then it's reasonable to look at the first passage time of this function by the reflected Brownian motion, because we look at the absolute value of this particle. And if we now look at the probability of that the first passage time of this deterministic boundary here is larger than t, then somehow this should be the same as looking at one specific particle which moves to the cloud of particles, and on the event that it hasn't been the maximum particle up to this time point t. But this means that this particle is in the set of particles which survived up to time t approximately, and by symmetry this has to be just a fraction of the surviving number of surviving particles up to this time divided by the initial amount of particles. This is not a proof, this is just heuristic. So, but we know at this time from the definition that this is just the number of order statistics which will fall above this value t, and from law of large numbers we know that this is converging to the survival function of the psi. So what we are looking for is now a boundary B which has the given distribution of psi. And this, to search for such a boundary is called the inverse first passage time problem, in this case for Brownian motion, or better reflected Brownian motion. So given the question is in this problem, given this random variable psi, does there exist a function B such that the first passage time over that function by reflected Brownian motion has a given distribution? And this was solved a long time ago. Sometimes it's working too much. And it was this was answered positively some years ago by Anulova with the answer yes, with the additional information that this function can be chosen lower semi-continuous. And so if we now assume that we really see this in this picture, then of course the question arises, do we see just one solution or the unique one, or is there something like uniqueness in this case? So, and the answer to this is that all solutions of this problem will coincide at this time interval here. This is the maximum reasonable time interval, so we have a reasonable uniqueness theory reside in these solutions. So somehow if we really expect that we will see this boundary evolving from this particle system, then we will see the unique one. But so let's continue with the particle system, and there is a very related particle system which inspired the considering of this work, and I want to explain this. So
this was called the N branching Brownian motion, short NBBM. And in this branching Brownian NBBM, we started author started with the Borsov process with rate n. So this is coupled with the amount of particles somehow. And then we look at the interarrival times as k. And we do a very similar thing. So we look at the following system where we start with n Brownian motions. And the largest particle here in this original literature, the largest particle is removed at the time points sk, so at the arrival times. But additionally, a bit more involved is that at this removal time we have an additional branching event. So one of the surviving particles, which is not removed, branches into two particles. So in this system we have constant size of particles of n, so constant amount of particles. So, and what was shown in this case is that when the particle size number grows large, then the empirical measure will converge to some deterministic measure which has a density, and this density was identified as a solution of a free boundary problem, and this free boundary problem is of the following form. So essentially just look at the first line. It's the free boundary problem described a density which the dynamic should follow that we want to solve a heat equation on the region below the boundary, but with additional mass injection at rate 1. And this is coming from Brownian motion hitting this boundary and then it's re-injected into the system. So, what has this to do with the inverse first passage diagram or with our process? So, this rate 1 injection corresponds to the fact that it turned out that this free boundary is the solution to, in this case, the one-sided inverse first passage time problem for the specific exponential distribution for the specific case. And so this was a very specific case, but they came up with a very good idea to analyze this part of the system. And I don't want to get into the details, but I want to show you the structure because this inspired the analysis of the more general system. So they started somehow to looking at the empirical measure here at specific time point, discrete time points delta k, where delta is some step size. And then they came up with some other stochastic process at this discrete time points, which bounded this empirical measure from the right and the left in the usual stochastic order. So this is just the usual stochastic domination order. And these are some couplings which they found above and below. So what's behind this? Then they proved these bounds here have also some deterministic limits. We will come to the more details later of this. And these deterministic limits will in the end go, when the step size is going to 0, go to the solution of the free boundary problem. And this means also that the term in the middle is going to the solution of the free boundary problem. And actually, this all of these errors here are somehow, to some extent, dependent on the fact that this was done in the situation of exponential distribution. But there's some more general picture behind it, and by this picture it was possible to prove for the particle system where we don't have branching, that for a general distribution psi, we have the following. So we again take these n time steps, and as in the heuristic argument, the essential condition was this convergence property here. And if we assume this convergence property on our removal times,
then we get the result that indeed, if we consider this system where we remove the particles at these removal times, that the empirical distribution of the absolute values of this process will converge to the law of the Brownian motion, conditioned to not have passed the solution of the inverse first passage time problem for this parameter distribution psi. Sorry, it was a long sentence. And so now I want to give you a slight idea of the proof. So yeah, some comments. So this means somehow that, so in the inverse first passage time problem, this B is highly non-explicit. You only know that it exists and is unique in some sense, but we don't know it. So this gives us a method to somehow simulate also from this measurement. So from something where this parameter B is generally really not known. Okay, so for the idea of some of the proof, so the good thing is in this, so remember this diagram, and the lower part of the diagram was we already analyzed this in the context of the general inverse first passage time problem. And there we did the following. So we defined these ratios alpha k, which somehow just correspond to the decay of the survival function of the psi in this discrete time step delta. So somehow we shift the mass of the psi just into the discrete time points. And then what was the goal? The goal was to approximate this measure somehow by something which only depended on the distribution of the psi. And this was done by defining the following measures. So it looks a bit complicated, but in fact it isn't that complicated. So we start with the initial distribution of Brownian motion. Think of just starting with point 0, for example. And then we do one step with the Gaussian kernel, so with the Brownian motion kernel. And then what we do is cutting off mass from both sides, but we exactly cut off truncate mass given by this alpha. And then we re-normalize by conditioning on this truncated interval, and then we do the same. So we go one step ahead with the Gaussian kernel, take the next truncation with the next alpha, and so on. And then we get this measure here, the one above. I can't go into the details what we are into some of the intuitions behind, but what I can say is if you revert this procedure that you first truncate and then convolute with the Gaussian kernel, then this some dual object which makes so this is somehow smaller than the measure we want to approximate, and this one is larger, so in the usual stochastic work. And then we were able to show that these measures, which only depend on the distribution psi, will converge to this conditional distribution of Brownian motion not having passed this inverse first passage time solution. So this is somehow the lower part of the diagram. And then now what is somehow lacking is the coupling of the stochastic processes. So I don't know what it is. So what we want to do somehow is to construct an empirical version of these measures, and this can be just seen as follows. So if we have in this process which lives on discrete time steps, if we then assume we have a set of particles alive, what we do one step ahead is to remove particles, not just one, successively we remove particles and look at the absolute value at the next time point, discrete time point, and we remove particles up to this point that we end up with the size of particles in the original process. So this corresponds to going one step forward with Brownian motion and then remove particles. It's like in the deterministic regime. And the dual object, of course, is this minus process where we have a part step where we assume at the discrete time step we have the set of particles alive. And then we remove particles and look at the absolute values at this actual time point. So really the time point delta k minus 1, and then take so that this equation is fulfilled, and then we look at the particles at the end of the interval at time point delta k. And so then you have to couple some particles to get some coupling which fulfills the ordering properties, but let me just explain why this is corresponding to being somehow empirical estimation of this deterministic measures. So let us just look at the case A plus. So let us assume here we have at this discrete time step the cloud of particles in this A plus regime, and then we start chopping off the large particles with largest absolute values above this point or at some empirical point, and we end up with a smaller set. And from the assumption on these definitions, by the assumptions on the removal times, we know that this ratio here actually goes to this ratio when n grows large. There is a condition on the removal times going in. And this is exactly was the deterministic ratio alpha k. So from this, somehow if you do this iteratively, it follows that this can be shown that then this empirical measure of this A plus regime, of these A plus particles will go, as n goes to infinity, will go to this deterministic measure here. And so, course of the time, I will skip the details of this A minus thing, but in the end we will end up with the full picture in this general case that there is a coupling, so you just have to manipulate some paths which are not really convenient in this setting. So there is a coupling that this minus particles will be the upper bound in this stochastic order, and the plus particles will be the lower bound. And then we have seen we have these arrows here on both sides, which go to the deterministic measures, and then we already have seen that then the deterministic measures go to the this conditional measure, and from this you can deduce that also the object in the middle goes to the target what we wanted to show. And this is the structure what is somehow behind the idea of the proof, so this is everything I wanted to show you. Thank you.
Thank you very much. Are there any questions, remarks? Okay.
Thanks. So if I understand correctly, so this particle system gives some kind of approximation or in the limit of the solution of the inverse first passage problem, and the barrier that would give you the exit time. So the inverse first passage problem seems quite similar to the Skorokhov problem, except that the inverse first passage problem is you're trying to find a barrier to have the exit time, whereas with the Skorokhov problem you're trying to find a barrier for the exit distribution. So have you thought about whether there's is there a way of changing the construction of this particle system so you can get a solution of the Skorokhov problem in the limit?
I haven't thought about this, but so here it's really dependent on this, that you really draw from this initial parameter, and this parameter was this given distribution. So I guess I think you think of what this Skorokhov problem solution where you construct this barrier set where the process somehow hits
It's it.
Yeah, and so I was wondering whether that value set can be formed in the same sort of way from a with a different construction.
So I don't know. So maybe one would have to consider some cloud of particles, but then from the storage problem, of course you can do it. I think the storage problem solution is also constructed by some limiting hitting time process, and then you could remove particles. I don't know. So
Another questions?
In one of your results, you had a condition on the times Ti, which was informed by the university to present before. This is probably not a very restrictive assumption.
You mean this assumption?
Yeah, right.
In fact, this is somehow the necessary assumption, because if you actually you can look at this empirical measure but not normalized to 1, but just by divided by n, so by the amount of initial particles, and then you will see somehow that if you just plug in here the whole space, then you will end up with the amount of particles alive at time 8t, and this is exactly this. And this has to go to the probability that the first passage time is larger than t, so somehow this is and this shall be exactly as it is, since b is the solution to the inverse first passage time problem. This then has to be this probability, so somehow this is a necessary one. So, yeah.
So if you were, let's say, to sample these times from C, would you?
How do I sample it then, or what is the question?
Let's say you have these times as independent copies.
Yes.
Of the random variable C. Would you expect this condition to hold them?
Yeah, so if you sample n samples independently from psi, and then order them so that you get the order statistics, then this is fulfilled. Because here the indexation is then, so the number of order statistics which fall above the time point t is exactly the number of samples which fall above this level t, this time t, so by law of large numbers we have these conversions. So maybe because to clear your confusion, so the only really reasonable other choice of time points is deterministic ones, in my opinion, where you choose this time point as some, just if you look at the quantized inverse distribution function of the psi, and then you produce exactly deterministic time points at quantiles 1 over n, 2 over n, and so on, of this inverse distribution function.
Thank you. Other questions? Now it's time to close our session, and I